Now let's study power system 1. For HVAC, we have different voltage levels that we need to keep in mind. That is 11 kV, 33 kV is for distribution line, and 66, 132, 220, 400, 765 and 1200 are for transmission. Okay, this one is for distribution and this is for transmission. And we use bundle conductor in case of very high voltage, for 220 we use 2 bundle conductor, for 400 we use 4 bundle conductor, and for highest, that is 765 and 1200, we use 6 bundle conductor. And we use 4 bundle conductor also for HVDC, that is for 500 to 800 kV. Okay, and HVDC is used for long distance. When it is like more than 500 kilometers, then we go for HVDC, because their losses are very less. Okay, because no skin effect and all. Okay, proximity effect is not there, so we prefer for HVDC. Okay, and when we do classification, classification are on the basis of length. Okay, on the basis of distance, that is short, medium and long. Short is when length is below 80, then we say short. If length is between 80 to 200, then we say it medium transmission line. If length is more than 200, then we say it long transmission line. Okay, so we can also find the relation of LF. Okay, LF, that is length into frequency. Just multiply it with 50, we will get the range. Okay, you will get this type of range. Okay, so according to this range also we decide short, medium, long transmission line. Okay, if we decide according to this, according to LF, then communication line is always a long transmission line, because its frequency is very high, and if we multiply with any length with that high frequency, then obviously we'll get the value of long transmission line. Okay, it will lie in long transmission line. So next we have transmission line parameter. Transmission line parameters are resistance and inductance in series, and capacitance and conductance in parallel. Okay, resistance we know very well, R is equal to rho L by A, and inductance we know, flux linkage per unit current. See out here, these phases are there. Okay, so there will be flux linkage. Due to this flux linkage, inductance is seen. Okay, and capacitance, see, air is between these two phases. Okay, so air as a dielectric, capacitance exists between lines. Okay, and also air as a dielectric, capacitance exists between ground. Okay, there are two type of capacitor. And when we talk about conductance is just a leakage current that flow in supporting structures. Okay, and next we have ACSR conductor. For ACSR conductor, just remember this two formula, that to find number of strands, 3x square minus 3x plus 1, where x is number of layers, and total diameter, to find total diameter, 2x minus 1 into d, where x is number of layers and d is diameter of each strands. Okay, and now we will study, now we will basically learn to find inductance of different combination of transmission line, like for single line, for single phase, 3 phase, double circuit line, etc. Okay, let us find inductance of single ACSR conductor. To find like when finding inductance of power transmission line, we will ignore the proximity effect and skin effect, because proximity and skin effect depend upon the frequency, and frequency out here is very less, that is 50 Hz, so its effect can be neglected. After neglecting that effect, we see that while finding internal inductance of ACSR conductor, in single ACSR, flux linkage is increasing in proportion to current from the center towards surface. Okay, so L internal remains constant, and that is given by 0.5 into 10 to the power minus 7 Henry per meter. And when you talk about inductance of ACSR conductor, it is for it is calculated into a see internal inductance and external inductance. Internal inductance is fixed, okay, that is this one, and external inductance is mu naught mu r upon 2 pi ln d by r, and d is where d is distance between the conductors and r is the radius of that conductor. Okay, this is external conductor. And when we talk about hollow conductor, it has no external internal. Okay, so this one also we can take it as hollow conductor. Okay, external. And when we talk about for solid ACSR, we will add these two. Okay, after adding these two, formula will remain same, only this r will change to r dash, and where r dash is 0.7788 r. Okay, r is radius of conductor. So this thing you need to remember. For solid ACSR we have this formula, and for hollow you know that internal part is not there, so only external, so this will remain same. Okay, so overall when we compare between solid and hollow, solid ACSR will have more inductance as compared to hollow. Okay, and we know that power flow equation, P equals to V1 V2 upon XS sine delta. So we can see that power flow is inversely proportional to the inductance. Okay, so if inductance is less, then power flow will be more. So according to that, here we can decide that here inductance is less, and therefore power flow of hollow conductor will be more than the power flow of solid ACSR conductor. Okay, this one we have. Okay, and next we have see in this chapter basically we'll find inductance, capacitance, and different many like parameters. Okay, so to find inductance, we know that L is equal to psi by I. Okay, flux linkage per unit current, psi by I. Okay, so for single ACSR conductor we know. Okay, suppose if there are many conductors. Okay, practically there are many conductors. Okay, like we have 3-phase system, double circuit line, there are many conductors now. So there will be flux linkage. Okay, so their inductance value will vary according to that. Suppose we have M phase. Okay, suppose we have M phase power system. Okay, suppose we have M phase transmission line. So to find suppose we have A, B, C, M conductors. Okay, and each of them has current IA, IB, IC, and IM. To find, suppose we we want to find flux linkage in IA. Okay, to find flux linkage in IA, we will do mu1 mu naught mu r upon 2 pi into IA. For first of all we will take for self. Okay, IA ln 1 upon r dash, where r dash we know very well, r dash is this one. Okay, upon r dash plus IB. Now we will take for IB. For self we took. Okay, after that we will take for IB an IB ln an IB ln 1 upon this distance. Then after that IC ln 1 upon this distance. After that plus IM ln 1 upon this distance. Okay, and remember that current should be balanced. Okay, IA plus IB plus IC plus IM equals to 0. Then we can find, this is the way to find flux linkage. Okay, we saw how to find inductance of single wire. Okay, now suppose we have single phase, okay, 2-wire transmission line. In that case, how to find inductance? See, total inductance, if we will talk about loop loop inductance, then obviously both line inductor will get added. Okay, so we already know for single ACSR conductor is mu naught mu r upon 2 pi into ln d by r dash. Okay, where suppose this we have two conductor. For single we already got. Okay, so for both if we talk about L loop, okay, then both will be get added. Okay, so we have multiplied it with 2. Formula remains the same, just multiplication by 2. It is very easy. This one is very important, and this is asked in exam for many times. Okay, this distance is given and r is given. After that they have asked to find inductance of this line. Okay, transmission line, so we can find it very easy to remember. Okay, next we'll talk about inductance for three-phase power transmission line. Okay, when we talk about three-phase power transmission line, there are different type of configurations. Okay, like it is horizontal, vertical, triangular, for like if the distance between them is d1 d2 d3, or it might be as a equilateral triangle d. Okay, so we have different formulas. So the same way as we done here, no, here also we will remember this way. This is inductance per phase. Inductance per phase mu naught mu r upon 2 pi ln multiplication of all the different distances. Okay, to the power 1 by 3. Okay, to the power 1 by 3 upon r dash. R dash is effective resistance. R dash is effective resistance. Okay, sorry, radius, it is effective radius 0.7788 r. Okay, therefore for equilateral triangle what we can do is same thing you have to do. Okay, multiplication of all this. After that we'll do, it will be 3 cube, and we have already 1 by 3. Okay, so after cancelling we will get finally this one. Okay, the inductance per phase you will get same like as that one, single phase. Okay, see, inductance per phase. So here we can see that inductance of triangular is less than inductance of horizontal. Okay, therefore we can say that power transfer in triangular will be more than the power transfer in horizontal. Accordingly remember that capacitance of triangular is more than capacitance of horizontal. Okay, so this one you have to remember. This one is for transposed. Okay, this one is for transposed. So when we talk about three-phase transmission line, we have two type of configuration. We have untransposed, okay, and we have transposed. Okay, this one was for transposed. Okay, what we studied. So let's see what is untransposed three-phase transmission line and transposed three-phase transmission line. Suppose when the three-phase transmission line is untransposed, we'll have radio interferences. Okay, radio interferences means electromagnetic interference and electrostatic interference. Electromagnetic interference will cause imbalance in current. Electrostatic interference will cause imbalance in voltage. Okay, and electromagnetic interference, see why this happens. Electromagnetic interference, suppose you have middle conductor, middle phase B will experience more flux linkage. Okay, if it experience more flux linkage, then obviously its current will get decreased. That's why current imbalance is seen in electromagnetic interference. Okay, see, middle conductor is having maximum flux linkage, so the current flow in this is decreased and current imbalance. For electrostatic interference, bottommost phase, that is C, will experience more electric field stress, so its voltage will increase. Okay, that's why we have voltage imbalance. Okay, see, bottommost part is more close to earth, that's why more experiencing more electric field. That's why its voltage is getting increased and imbalance in voltage is seen. Okay, and So if we do transposition of this line, okay, this way you have to do transposition. Here all phases experiences same amount of EMI and ESI, electromagnetic interference and electrostatic interference. Okay, all the phases will have the experience of same amount. Okay, that's why current and voltage will remain balanced. Okay, so sum of current will be 0, sum of voltage will be 0. Okay, so this is the thing that we need to keep in mind. Now let's find out inductance per phase of bundle conductor. Okay, while finding out inductance per phase of a bundle conductor, we have to use same formula as we studied for single phase, three phase. Okay, only difference will be that we will replace D. We had like ln d by r dash. Okay, and d was distance between conductor and r dash was effective radius. Instead of distance between conductor, we will be using GMD, that is geometric mean distance, and instead of effective radius we will be using geometric mean radius or self GMD. Okay, GMD and GMR. Okay, GMD is geometric mean distance and GMR is geometric mean radius. Okay, we will be using this. So in this topic, basically our main challenge will be to find out GMD and GMR. Okay, if we are able to find GMD and GMR, then everything to find inductance is very easy. It's not a big deal. Okay, it's like same as previous, mu naught mu r upon 2 pi ln DMAB means mutual GMD. Okay, mutual GMD upon this one is self GMD. Okay, so here also see mutual GMD upon self GMD. Formula remains same. Okay, formula remains same. So mainly we'll focus here to find out GMD and GMR. Okay, suppose we have two phase. Okay, suppose we have phase A and phase B. Okay, and phase A has m conductors bundled together. Okay, like A, B, C, M. Okay, we have phase A with m conductor bundled together, and we have phase B with n conductor bundled together. Okay, let us see how to find GMD. Okay, geometric mean distance. Let's find geometric mean distance. Okay, sorry, first of all let's find GMR, geometric mean radius. Okay, geometric mean radius. See, for to find geometric mean radius for phase A, what we have to do is see here, to find geometric mean radius of phase A, we'll just multiply self effective radius, effective radius of that conductor phase A, an effective radius of conductor A into distance between AB, distance between AC, distance between AM. Okay, and this will form this much. Okay, and after that again for B, taking this as reference, radius of B into distance between this, distance between this, distance between this. Okay, whatever is there in phase we will take. Okay, for self, and for similarly for C, radius of this into distance between this, distance between this. Okay, and for M, radius of this into this one distance, this distance, this distance. Okay, in this way. So finally we will get finally we will get this. Okay, after getting this and we will do whole to the power 1 upon an m square, that is number of conductors in phase A. Okay, so similarly we will find for phase B also. Okay, similarly we will find for phase B, and to find mutual GMD. Okay, to find mutual GMD, what we have to do is, suppose we want to find mutual GMD between A, B. Okay, conductor A and conductor B. So DMAB will be same as DMBA. Okay, these both will be same. Let us find. We'll take this distance, this distance into this distance into this distance into this distance. Okay, similarly for when we take reference this distance into this into this into this, okay. When we take reference this into this into this into this, okay. When you take reference m, then this, okay. So in this way we will do. So after that we will get this one, okay. And whole to the power 1 upon m into n. M is number of conductor in phase A, n is number of conductor in phase B. So similarly we will get GMD and GMR, okay. GMD and GMR, in this way we will get. So after that we will put in the formula, instead of D and R we will put GMD, and instead of R dash we will put GMR, okay. So when we talk about for two bundle conductor, to find GMD for two bundle conductor, let us see how to find GMD for two bundle conductor. GMR of two bundle conductor will be just this one, okay. Just S will be the GMR, okay. So main thing here we have to find is GMD, okay. Suppose we have bundle conductor A and B is phase A and it is bundled together, okay. To find GMD, what we'll do is we'll take radius of A, into distance between them, okay, and again radius of B into distance between them. So finally we will get this one, okay. So then effective radius is R dash into S to the whole square, okay. We will get that to the whole square, and whole to the power, what we do, 1 upon 2 square, okay. 1 upon 2 square. So square will get cancelled due to 2 is there inside, okay. So finally we get this one. So similarly we have to do for bundle conductor 3 also, 3 bundle conductor also, okay. Self radius into this distance, so R dash into R dash into S square. So similarly we will take as a reference this also. So finally we will get this one, okay. So similarly we will find for 4 bundle conductor, and for stranded conductor also we can find this way, okay. It's very easy, you can find this way for stranded 2 conductor, for 3 stranded conductor, and for 7 stranded conductor, just remember, okay, 2.176 into R. This is effective radius, okay. And so finally let us know the advantages of using bundle conductor. If we do bundling then self GMD will increase, means GMR will increase, okay. If we do bundling, then self GMD will increase, okay. If self GMD increase, then inductor will decrease. Then inductance decrease. If inductance decrease, then power transfer capacity will increase, okay. And second one is corona loss will decrease, radio interference will decrease, cost of power transmission decrease, and material required decrease for same power transfer, okay. And when we talk about surge impedance, that is root L by C. When L will decrease, then Z will also decrease, that is surge impedance will also decrease. And for surge impedance loading, IL equals to V square upon ZS. If ZS decrease, then IL will increase, okay. So surge impedance loading increase, surge impedance decrease, and surge impedance loading will increase, okay. And ESI, electrostatic interference, will decrease because voltage gradient is very less due to the area of conductor is less, okay. So this thing you need to remember. So next, inductance per phase of a double circuit line, okay. See, this is double circuit line. We have RYB and RYB, okay. If we will place RYB in this form, okay, if we will play in this form, then see GMD of this one will be less, okay. GMD of this one will be see, GMD of this one will be less than this, okay. GMD of this will be higher, okay. GMD of C, if we place this way and if we place this way, this GMD due to increase in distance between R1 and R2, GMD, self GMD will increase. Okay, we know that advantage of increase in self GMD very well. If self GMD increase, L will decrease. Okay, if L decrease, then power transfer capacity will, that is good, but radio interference will still be here. Okay, self GMD is increasing, but radio interference is still there. Like we see in three-phase circuit line, no, same type of radio interference will be there. Okay, due to this one will have more flux linkage, so current flow will be less, so current imbalance, and this one is close to ground, so this one will have more electric field in field effect, and its voltage will decrease, so voltage imbalance. To avoid this, we do transposition. Okay, to avoid this, we do transposition. And to find inductance per phase, we just remember mu naught mu r upon 2 pi ln and dm1 dm2 dm3 upon ds1 ds2 ds3 whole to the power 1 by 3. Okay, this formula you need to remember for this. And now we will learn how to find capacitance. Okay, capacitance is charge accumulated per unit voltage. Okay, well, let us see for capacitance of single ACSR conductor. Okay, if we have suppose we have a conductor. Okay, single ACSR conductor, and we want to find its capacitance at a certain distance. Okay, just we have this, suppose we have this conductor, and we want to find capacitance at this point. Okay, at this point we find capacitance. So remember these two formula. Okay, voltage will be Q, that is charge on the capacitor. Okay, Q upon 2 pi mu naught mu r ln d by r. R is the radius of this conductor, Q is the charge on this conductor. Okay, on the surface of this conductor, and D is the distance between this point. Okay, this is the meaning of. Okay, to find V, if we got V, then we can find C. How we can find C? We know that Q is equal to CV. Okay, Q equal to CV, therefore C equals to Q upon V, and we know already Q value. Okay, we know already Q value, therefore Q upon V will be C. Okay, now when we will divide this thing with Q, and then we will get this. Okay, it will go up and Q will get cancelled, so 2 upon mu naught 2 upon epsilon naught epsilon r upon ln d by r. Okay, D is distance between them, and radius of this conductor. Okay, and epsilon naught value is 1, epsilon r is 8.85 into 10 to the minus 12. Okay, so similarly we can find capacitance of a single phase 2-wire transmission line. Okay, to find capacitance between A and B, suppose we already know capacitance of single wire. Capacitance of a single wire is this one. Okay, capacitance of a single wire in here also, see, per phase is this one. See, matching. Okay, when we will find capacitance between these two, then we will just divide this by 2. Okay, we'll just divide it by 2, then we will get CAB. Okay, capacitance CAB. We have got pi epsilon naught epsilon r upon ln d by r. See, same thing is there, it is just divided by 2. In case of inductor, what we had, in case of finding inductance of a single and it's same like when we found for loop, we multiplied by 2. Okay, but here when we will include both, then we have to divide by 2. Okay, remember that in case of inductor and capacitor. As we found flux linkage in case of in case to find inductor, here also we have to find voltage between the conductors to find capacitance. Okay, see, if we have more than one inductors, when we have more than one conductors, then how to find voltage between A and B. Okay, let us see that how to find voltage between A and B if we have A B C M conductors. Okay, So for that we have formula VAB equals to 1 upon 2 pi mu naught mu r into, first of all we will take for self, okay. For A we are taking QA ln D is this distance and R is effective radius, okay, effective radius. And similarly for QB into ln R is effective radius and D is distance between them. QC into this distance into QC into ln this distance upon this distance, okay. Similarly plus QM into ln this distance upon this distance, okay. And remember that QA plus QB plus QC plus QM should be equals to 0, okay. And effective radiance, now let's see effect of earth on capacitor between conductors of transmission line. Effect of capacitance increases, okay, due to earth, okay. See, from this formula we can make out CAB equals to pi epsilon naught epsilon R ln D by, and this one is R root 1 plus D square upon 4h, okay. See, when height of from this formula we can make out that capacitance is inversely proportional to effect of earth on capacitance is inversely proportional to height of tower. If the height of tower is less than effect of then the capacitance will increase. If the height of tower is more, then the effect of earth on capacitance will decrease, okay. This thing you need to remember. So here we have the table for voltage. For every voltage level we have different height of tower. See, we can see that as voltage level increases, height of tower also increases. So we can see we can say voltage is directly proportional to height of tower. As voltage increases, height of tower also need to be increased, because we need more clearance as the voltage increases due to decrease the effect of capacitor, okay. So next, see, this one is the formula. This one is a very important thing, okay. This one we have to mug up only, okay. Have to keep in mind all the time. So like for we have different configurations, and for that we have to find inductance and capacitance, okay. It is very easy to remember this. For single ACSR we know very well mu naught mu r upon 2 pi ln D by R dash, okay. And for capacitance what we will do is that for capacitance we will do 2 pi epsilon naught epsilon R upon ln D by R, okay. And here we have R and here we have R dash. This is effective radius, that is 0.7788 R, okay. And this one is direct R, okay. So this thing you need to remember. This difference need to be remembered, okay. Similarly for single phase 2 wire system we have mu naught mu r upon 2 ln D by R dash, okay. It will be same, okay. And in here also it will be just divided by 4 per phase. This one is for per phase. This one is for per phase. You know that in case of capacitor it will be divided by 2, and for loop it will be into 2, okay. For inductor it will be into 2 for loop, okay. And similarly for three phase transposed in per phase, okay. Three phase transposed in per phase we have see 3 phase transposed in per phase. We will do mu naught mu r upon 2 pi ln and d1 d2 d3 whole to the power 1 by 3 upon R dash, and here it will be R, okay. Here it will be R, okay. Only R will be here. 2 pi epsilon naught epsilon R upon ln d1 d2 d3 upon R dash whole to the power 1 by 3, okay. See, we have only difference is that here we have to just flip, okay. Flip this 2 pi up and ln d by R down, okay. We just have to flip everywhere. We have done the same, okay. Difference between L and D. So for triangular we have same distances, so we will get this one, okay. We have same distances, so we are getting this. So for bundle we know that instead of D we write mutual geometric mean distance GMD, and for R we write GMR. Okay, and here also same, here also see everything is as it is. Okay, we are just flipping these 2 pi and ln dy r. Okay, so these are the differences. Okay, when we talk about surge impedance, surge impedance is represented by ZS, that is root L by C. It is constant throughout the transmission line. Okay, surge impedance is constant throughout the transmission line, and for overhead transmission line, surge impedance is between 300 to 500. Generally we take value 400. Okay, and for cables we have surge impedance 40 to 50 ohm. Okay, and velocity of signal. Okay, velocity of signal in the transmission line is given by 2 pi fl upon root under, that is b into xl. Here b is susceptance and this one is reactance. Okay, 2 pi fl upon root b into xl equals to 1 by root lc is equal to this one is speed of light, 3 into 10 power 8 meter per second. Okay, remember this thing, velocity of light we know that 300 milli per microsecond, and velocity in overhead line is between 200 to 250 meter per microsecond, and this one is 40 to 50. Okay, 40 to 50 range. Okay, meter per microsecond. Now let's understand resistance. Okay, remember that resistance in AC is more than resistance in DC. Okay, for the same conductor, resistance in AC is more than resistance in DC. Why is it so? It is due to skin effect and proximity effect. Okay, due to skin effect, more flux linkage is at the center. Okay, due to skin effect, conductors have more flux linkage at the center, so L increases and XL increases. Okay, due to this increment in L and XL, current flow at the center is very less. Okay, due to more flux linkage, current flow at the center is less, and due to this less current flow, so effective area of conductor current flow is reduced. Okay, if effective area of the conductor will reduce, then obviously RAC will increase. Okay, resistance will increase. Proximity effect is like due to a portion of conductor that is in proximity of another conductor has more flux linkage. Due to this more flux linkage, so effective area of current flow will be less. Okay, due to which resistance will increase. Okay, due to which resistance will increase. And remember that in inductance calculation of transmission line, skin effect and proximity effect are neglected, so L is constant throughout the area, and neglecting because frequency is very less, that is 50 hertz. Okay, and when we talk about skin depth, it is dependent on del. Okay, and delta skin depth of a conductor at which Imax drops to 1 upon E times. Okay, Imax drops to 1 upon E times. It is the depth of the conductor at which maximum current drop to 1 upon 2 times. Okay, 1 upon E times, and it is given by the formula 1 upon root pi f mu naught mu r sigma. Okay, and is directly and skin depth is inversely proportional to skin effect. Okay, if skin depth is more, then skin effect will be less. Okay, if skin depth is more, then skin effect is less. If skin depth is less, then skin effect is more. Okay, and finally we have conductance. Conductance means just a current leakage through the structure. Okay, through the tower structure. Inductance is neglected for short and medium transmission line. Consider only for long transmission line. Okay, G is considered only for long transmission line, And when we talk about transmission line, now let's study transmission line parameters. Okay, we know that resistance and inductance are in series, and capacitance and conductance are connected in parallel this way. Okay, so it seems a very complex network. Okay, so we take assumptions. System is balanced and symmetrical. Okay, so we are taking assumption that system is balanced and symmetrical. So we can do calculation on per phase basis. If three-phase system is symmetrical, then we can do calculation per phase basis, we know very well. Okay, so when we'll do per phase calculation, we have this. Okay, we are taking a phase R. Okay, let's take phase R and its reference with neutral. Okay, and so we have sending in, receiving in, and we have distributed long transmission line. See, in case of long transmission line, all the parameters are present. Okay, in case of short and medium, G will be eliminated, and in case of in case of short, C and G both are eliminated. Okay, because voltage is less out there, so effect of capacitance and inductance decreases, and in medium in short, effect of conductance is eliminated. And similarly we can write as a lump. Okay, for suppose we have to write lump parameter for 100 kilometer. Okay, and we have been given value of RLCG for per kilometer per phase. Okay, and we can just multiply by 100 and we can write it like this. Okay, lumped. Okay, so this is the way. So we saw long transmission line. Now let's see medium transmission line equivalent circuit. Here G is very small, so we neglect it. Okay, so this is the way to represent medium transmission line. It can be represented in three ways. Okay, that is end condenser network, nominal pi network, and nominal T network. This way. Okay, this way we have to represent. Okay, say. And for short transmission line, C and G both are very small, so we neglect it. Okay, so we have this. It's very simple short transmission line. And now let's study about ABCD parameters of transmission line. Okay, ABCD, or we can say transmission line parameter. Okay, so ABCD. So we know we have studied in network that it is similar to that only. Okay, only difference out here is in network we were putting this direction. Okay, and sign of this IR was minus. Okay, but here we are just changing the sign, direction of current, and changing the sign. Okay, if we change direction of current, then we can change it to plus. Okay, so this way we have done. Okay, so finally we can get equations from here for sending in voltage and sending in current. We can get from here. Okay, sending in voltage will be A into VR plus B into IR, and sending and current will be IS equals to C into VR in plus D into IR. Okay, and remember that if A equals to D, then the parameter is reciprocal, and if AD minus BC equals to 1, then it is symmetrical. Okay, and when for cascade network, if they are connected end to end, then we can just multiply it and get a equivalent. Okay, we just have to multiply these two metrics to get a single ABCD parameter. Okay, and similarly for parallel we do. So similarly for parallel we have to remember this formula. Okay, for A we have A1 B2 plus A2 B1 upon B1 plus B2, and for D we have D1 B2 plus D2 B1 upon B1 plus B2, and for B equals to B1 B2 upon B1 plus B2, and C equals to C1 plus C2 plus A1 minus A2 into D2 minus D1 upon B1 plus B2. Okay, this one we have to remember cascade and parallel. Okay, and I remember this for remember this for impedance network, this one as an impedance network. If you see this type of impedance network, then you can represent this as this, okay, 1Z01, okay. And if you find this type of admittance, then you can replace this by this matrix, okay, 10y1, okay, 10y1, this, okay. Remember these two things, impedance and admittance, okay. So from here you can use this and find for medium, nominal pi and condensed knot, okay. Using this you can find very easily. Suppose we have medium transmission line. Here we can say this is impedance, admittance, impedance, okay. Just multiply this, okay, because you can say it's like cascade, okay. So we can multiply. After multiplying this thing, you get this value, okay. So this one is the representation of nominal T network, okay. So similarly we have admittance, impedance and admittance. See, admittance, impedance and admittance. So after multiplying this, we will get this answer, okay. So similarly for and condensed knot, here we have impedance and admittance. Just multiply this, okay, you will get this, okay. So similarly we just have, you can remember this also, okay, 1 plus yz by 2, z into 1 plus yz by 4, y 1 plus yz by 2. See, this one is same, okay, 1 plus yz by 2, 1 plus yz by 2, okay, is same for pi and t, okay. Only difference is that this one is getting reversed with y out here, with y, and here we have z, and 1 plus yz by 4 we have, okay. This thing you need to remember. No such difference, is just we are putting this thing out here, okay, for this one, and we have 1 plus yz, z, y1, okay. This way we have to remember. So similarly for long transmission line, you have to remember VSIS equals to cos h cos h what is this, psi l, okay. So this one is propagation constant, okay, propagation constant L, okay. This we have to remember ZC sin h psi L, sin hyperbolic psi L upon ZC, and cos hyperbolic L, okay. This way you have to remember, and this thing you need to remember, no option is there, okay. So remember this. And for power flow equation of transmission line, you can relate this with previously what we studied in alternator, okay. You can easily relate with. So just remember about the ABCD parameters are this, okay. And these are their notations, okay, given. Alpha is this one is propagation constant, also given by alpha plus j beta equals to root z1 y1, and alpha is attenuation constant, and beta, and here beta is phase shift constant, and z1 is r1 plus j omega l, y1 is g1 plus j omega c, zc is characteristic impedance equals to root z1 upon y1, okay. And power flow equation, when we talk about power flow equation of transmission line, we have sending end power flow equation, and receiving in power flow equation, and sending in power flow equation, okay. This power flow equation is applicable for short, medium and long transmission line. To remember this thing, remember by relating with generator equation of synchronous machine. Only difference is that in synchronous machine, and this a alpha is not there, and d alpha is not there in case of sending end, and a alpha is not there in case of receiving end, okay. There we had power output in case of receiving end, and in case of sending in we have power developed, okay. So it's a similar kind of equation. Only difference is this part is not there. Okay, this one, this one is this one, and this one is not there, and this one is replaced by this b angle beta is replaced by z angle theta. Okay, only this is the difference. Everything remains same. So if we know this one, if we know this one, from here we can easily find active power and reactive power by putting here cos, and by putting here cos and sin. Okay, cos for active power, sin for reactive power. Okay, so from here you can get all together 4 equations. Okay, if you remember these two. So similarly, when we talk about objectives of transmission line are basically transfer maximum power with minimum losses. Okay, so our objectives will be to design a transmission line in such a way that it should transfer maximum amount of power and minimum amount of loss should happen. Okay, and also voltage regulation to be as minimum as possible. Okay, and these two are the objectives, main objective of transmission line. Okay, how we can do that, we will study in this syllabus. Okay, so when we talk about receiving voltage regulation to be minimum as possible, ideally it is voltage regulation is 0. Okay, but practically it is between 5%, plus minus 5%. Okay, voltage regulation is basically, we know voltage regulation, no load minus full load upon full load into 100. Okay, so here also it is the same. Okay, no load minus full load upon full load into 100. Here no load, only difference is out here is no load is replaced by Vs. Okay, Vs is standing. Okay, that is also no load only, but here we have to divide by A. Okay, the transmission line parameter. So we will divide it by Vs upon A minus VR upon VR into by putting mod on each. Okay, and into 100. So here we have transfer maximum amount of power with minimum load. This we can obtain by if we see the equation from here, you can make out what we have to do to achieve this kind of thing. No, see, we know sending in power, receiving in power is equal for short transmission line. We're talking. Okay, and Vs is equal to RS. Vs equals to Vr. Okay, Vs equals to Vr. So we can write it as Vs square upon XL sin delta. And here we can clearly see, if we decrease XL, if we decrease the reactance of transmission line, we can increase the transfer capacity. Okay, and if we increase the voltage, transmission line voltage, then we can also increase the power transfer capacity. And if we can increase the delta, then we can increase the transfer capacity. Okay, these 3 things are here to vary. Okay. So remember this advantage of let us see advantage of increasing voltage and method to reduce reactance, that is XL, and importance of power angle. Okay, let us understand each one by one. First of all, let us see advantage of increasing voltage. If we increase voltage, then obviously first advantage will be we can send more amount of power. Okay, and second advantage is that losses will be minimum. Why losses will be minimum? Because we know that loss equals to I square R, and I equals to from power equation, P is equal to VLIL cos theta. Okay, VLIL cos theta. Therefore I equals to P upon V by I. Okay, P I, and I equals to P upon V cos theta. So I square into R. So here we can see the relation. If we are increasing the voltage, power loss is getting decreased. Okay, it has an inverse relation with power loss. Voltage has inverse relation with power loss. Okay, square of voltage. Okay, this thing you need to remember. Okay, so for power loss, And for area also it has an inverse relationship. Conductor size will reduce, power loss will decrease, conductor size will also decrease. Okay, from here you can make out area equals to rho L by R. Okay, and R is this one is R. Okay, from here we found R. Okay, this one is R. Okay. So from here we can see they are inverse relation with square of voltage. Okay, power loss and area are inverse relation with square of voltage. Okay, square of voltage, and this one is direct relation with power transfer capacity, direct relation with voltage. And only limitation of voltage increment is that insulation will increase. Okay, amount of insulation that we apply will increase, so cost will increase. This is only the limitation. And now let us see how to decrease the XL value. XL value can be decreased by obviously by bundling of conductors. Okay, and also by double circuit transmission line, also use double circuit transmission line. And third one is add a series capacitor, but only up to 40 to 50%. Okay, because otherwise if we add more than 40 to 50%, then there is chance that the generator might fail. Okay, so we do not do so. We will only increase up to 40 to 50%. Okay, compensation is done with this using series capacitor. Okay, compensation reactive power. Compensation of reactance. Okay, so importance of power angle delta. Okay, power angle is angle between rotor field axis and stator rotating RMF. Okay, stator rotating magnetic field, angle between rotor field axis and stator rotating field axis. Okay, and power angle need to vary according to the changing demand of load. To increase delta, we increase steam input. Okay, and stability limit of power angle is 55 to 60 degree. Next let's understand procedure for calculation of performance of transmission line. Okay, this one is important. Okay, this one because questions are asked from this in GATE and also in ESE. Okay, so remember this. We will be in question, we will be given this type of structure. Okay, this type of information we will be given like power, active power of load and its power factor. Okay, active power of load and power factor will be given, and receiving end voltage will given, and ABCD parameter or RLCG will be given. Okay, this or this will be given. Okay, total of 1 2 3 things will be given out here. Okay, so we will be asked to find what is the efficiency. Maybe we can be asked to find what is power loss. Maybe we can asked to find what is voltage regulation, or they can ask us what is the sending end voltage. Okay, what is the receiving end current also they can ask. So let us see how to solve this. Okay, this is very easy. First of all, see, if ABCD parameter is given, then it's okay, we'll use that only. Okay, if ABCD parameter is not given and RLCG is given, then from that we will make ABCD parameter. Okay, you know very well how to make ABCD parameter for short, medium and long transmission line. It will be given in the question how long is that transmission line. According to that we will decide in which category it comes. Okay, so accordingly we will find ABCD parameter. Okay, from the given type of transmission line. So second step will be to find the receiving end voltage. Okay, we will find this one. Okay, second step we will find this one. How we will find this one? We know that power is given, power factor is given. P equals to root 3 VL IL cos theta. Okay, root VL IL cos theta. It should be phi r, okay, phi r root 3 VL IL cos theta. So therefore IR will be PR3 phase upon root 3 VRL upon cos theta. This one will be given line voltage, okay. So here we can use for line voltage itself, okay. So IR we will get, and cos theta means power factor. So from power factor we can get by doing inverse, cos inverse we will get the angle also. So IR angle we will get also, okay. So we got IR. So now next let's find receiving end voltage. We know that Vs equals to AVR plus BIR, okay. This equation we know from ABCD parameter, okay, matrix of ABCD parameter. So here we have here basically we have Vs phase, okay. Vs phase will be A into VRL. It was line, no, so we will convert this into phase, okay. So we know that calculation is done per phase, that's why we are doing this, okay. By dividing it by root 3, and VRL and VPH is and IRL and IPH is same, so we can use IRL itself, okay, because it's star connected, okay, star connected, that's why this load is also star connected. We are doing per phase calculation, okay. As VSPH sending end voltage we can find this way, and angle we will also get at the same time. So similarly we can find sending and current, okay, sending and current also from that equation only, ABCD parameter, okay. C into VRL plus D into IR, okay. From there you can get, okay. So similarly we'll put this one is theta 1 and this one is theta 2, okay. From here, see, we can easily find theta s, means angle between sending end voltage and sending end current you can find, okay. So if we get theta s by doing theta 1 minus theta 2, okay, so we can find sending end power we can easily get, okay. Root 3 VSL ISL, okay, root 3 VSL ISL cos theta s, okay. This theta s we will use here, okay, cos theta s. So then we can easily find efficiency, because we already know output power and input we have found here, okay. So efficiency will be output upon input, okay, into 100, and power loss we can easily find input is given, input we found, and output is already given. So input minus output will be power loss, and voltage regulation we can easily find VSL we found from here, okay. VSL VPH from here we can find VSL, okay. VSL upon A minus VRL is given, okay. VRL upon VRL into 100, okay. This way we can find it. See here, and if you use phase voltage, no, then we have to use this as for also all should be phase or all should be line, okay. So we can find easily, okay. This is the way to find. If you wanna see, let's see one example, okay. See, in this question the per phase parameter 50 hertz 100 kilometer long 3-phase transmission line are R, L, C. The transmission line delivered 20 megawatt of power factor 0.866 kV to balanced load, okay. Calculate sending end VS, okay, sending end voltage efficiency and voltage regulation. See here we have given RLC, okay. RLC and 100 kilometer line means what? 100 kilometer line means medium, okay. It lies between 80 to 200, so medium. And we know that medium transmission line, and in here we are told using T network. We know easily how is the T network. T is T network is resistance reactance, and in between we have capacitor and then resistance reactance, okay. From there you can easily know find the ABCD parameter is this way, okay. 1 plus yz by 2, 1 plus yz by 4 into z y, 1 plus yz by 2, okay. From by putting the value of z we can find out from here, okay. Z means this one, okay. Z means resistance, like resistance inductance, okay. Resistance inductance so from resistance inductance, no, you can get Z. Okay, resistance inductance we can get Z. Okay, and from the capacitance we can get the inductance. Okay, so after getting that value, just put in this and we will get ABCD parameter. After getting ABCD parameter, we can see. Okay, after getting a ABCD parameter, we will find IR. IR we can immediately find. Okay, without finding ABCD also. Three phase power upon root 3. Okay, this way we can find. It's very easy. Okay, so sending end voltage, to find sending end voltage, no, we need this equation. Okay, see, VPH equals to AVR root 3 up plus BIR. Okay, so we'll put all the values, all are given out here. Okay, VRL is given. Okay, and IR we have found, and A is given, B is given. Okay, B like A and B we have found here. Okay, and so we can get VSL. Okay, and angle also we can find that angle represented by theta 1. And fourth number, we have sending end current. Okay, sending end current, IS equals to IPH equals to C. This also we can get very easily. Okay, VRL is given, IR is given, and C is here, D is here. Okay, by putting this we can get. Okay, and similarly we can get phi S. Okay, phi S, see, this one I am talking about. Okay, similarly we are given with phi S. From here we can find. Okay, phi S. So sending and power we can find very easily. Okay, this way we have to do. Okay, loss, and this is the way to do. So in per unit system you have to remember some basic formulas. Okay, suppose we have S base and voltage base. Okay, MVA, S base in MVA, voltage base in kV. Okay, selected base. Okay, and we have to find, suppose we are given Z or R or X in ohms. If you want to find ZPU, you know that Z per unit is actual upon base. Okay, this one is actual and this one is inverse of base value. Okay, base Z base. Okay, you know that Z base is V square by S. Okay, V square base by S base. Okay, so we have inverse, we have directly written here. Okay, so in the same way we can find for Y per unit also, and you know very easily to find Z per unit from old, we can ZPU new equals to ZPU old into SB new upon SB old into VB old upon VB new whole square. And and this one is important to remember. Okay, generator parameter, when this HPU and MPU is given here. HPU and MPU is basically, let us see what is HPU and MPU. Okay, here MPU is inertia constant and HPU is angular like angular momentum. Okay, to find a new MPU, we have to find by old MPU into old base, old power upon new power. Okay, and similarly for HPU old upon SB old upon SB new. Okay, and for motor equivalent, if to find motor equivalent, if series RLC, to find series RC circuit, ZPU equals to SB upon S, that is motors MVA of motor into cos theta plus J sin theta. Cos theta we can get, it's a power factor, cos theta is power factor, and from power factor we can get the angle, and by that angle, by putting in sin theta, we will get J sin theta. Okay, so we can get RPU plus J XPU. Okay, similarly for parallel we will do directly SB upon S cos theta, and xpu equals to sb upon s sine theta. Okay, sine phi. Okay, it's phi. Okay, not theta, phi. Okay, so this way you have to remember. Now let us see voltage regulation for uncompensated transmission line. Uncompensated transmission line means any reactance, resistance is not connected in series or parallel with the transmission line. Okay, it means uncompensated transmission line. Let us see for short transmission line. Short transmission line we know very well. Okay, see to know about this, to remember this voltage regulation, you need to take reference of voltage regulation that we studied in transformer. Okay, it is similar to that only difference is here is here we have transmission line. Instead of transmission line, there we have a transformer. Okay, and load we know that we have lagging, unity, like a leading power factor load. Okay, this type of load. And voltage regulation means no load voltage, that is vs minus vr mod upon z vr mod. Okay, and equals to, we know that this one is rpu xpu, rpu sin cos theta cos phi r plus minus xpu sin phi r. Okay, and this one, and here we use plus for lagging, minus for leading. Okay, this you have to remember. This equation is most important. Many things we can prove from here. Okay, so for lagging load, only positive voltage regulation. Okay, and at the zero power factor, purely lagging, we get percent x. Okay, is x voltage regulation, this we get. And for unity only positive voltage regulation, that is percent r. And leading load, that is positive voltage regulation, very high power factor, this we get at very high power factor only. And for zero voltage regulation, high power factor, we get okay, zero voltage regulation can be only obtained in from leading load. Okay, and negative voltage regulation can be obtained from leading load, very low power factor leading load. Okay, for zero power factor leading load, we have minus percent x. Okay, condition for maximum voltage regulation, remember this, occurs only at lagging load. Okay, and condition is that load impedance angle, that is phi r, should be equals to transmission line impedance angle, that is theta. Okay, and if it is so, then we can say a power factor of load equals to power factor of transmission line. Okay, and maximum voltage regulation is given by zpu, z per unit. Whatever the z per unit of transformer we will get, no, that will be the maximum voltage regulation. And when you talk about condition for zero voltage regulation, occurs only for leading load. Okay, remember that it occurs only for leading load when load impedance and sum of load impedance angle and transmission line impedance angle equals to 90 degree. Okay, so we can see this triangle. Okay, impedance triangle. See, this one is transmission line parameter. Okay, transmission line parameter r, xl and z. Okay, and similarly we are given with theta. This is a transmission line impedance angle. And this one is the, when we see from here, no, this one as a base and this one as a perpendicular, and this one as a angle of load. Okay, so we get impedance triangle of load. Okay, so we have cos theta r equals to sine cos phi r equals to sine theta r equals to xl by z. Okay, so this one relation we have to remember. When we take this one as a base, then it is transmission line impedance triangle. When we take this one as base, then it become load impedance triangle. Okay, this is the funda out here, so remember this. Now let's study voltage regulation in medium transmission line. When medium transmission line is connected with a lagging load. Okay, remember that medium transmission line, for medium transmission line, whether it is pi network or T network, voltage regulation will be positive, and Is will be less than Ir for both. Okay, and for pi network, Is is less than Ir due to charging current ICR and ICS. And for nominal T network, Is is less than Ir due to charging current. Okay, in between the transmission line, we know that we know the configuration of transmission line, how is it in this. Okay, to get more clear ideas, see this one. Okay. To get more clear idea, see here we have proved the voltage regulation using phasor diagram. Okay, using, this is the pi network and this is T network. See, let us explain the for pi network. Okay, first of all, we will take a reference. Okay, VR as a reference. We took VR reference. Okay, this one is VR. We took VR reference. After that, load is lagging, that's why we will take current as a lagging. Okay, so IR will be lagging. See, this one is IR. Okay, we took IR current. Okay, after that what we have, ICR. Okay, ICR, and with respect to VR, ICR will be leading because it is purely capacitive, so it will be leading. See, VR is this, and it will be exactly to 90 degree ICR. Okay, this one is ICR, and same we will put here. Okay, ICR will come here. Okay, after that when we will join ICR and IR, ICR plus IR will be what? IL. Okay, so we will get IL. Okay, so see, this one is IL. Okay, we got IL. Okay, so after getting IL, we will add the drop of resistance and inductance. Okay, resistance drop will be in the same phase. Okay, resistance drop will be in the same phase, and inductance drop will be leading. You know that voltage will lead. Okay, and current is lagging in case of inductor, so it will be leading. Voltage IL will be IL XL will be leading like this, and IR will be in the same phase. See, same we will put here on the voltage, IR in the same phase, and this one is leading voltage. Okay, so IL XL leading, and when we will combine this, we will get Vs. Okay, see, Vs, after getting adding this drop, we will get Vs. After getting Vs, we can see that ICS is purely leading. Okay, purely leading with Vs. See, purely leading with Vs. Okay, we got purely, and we will take the same thing here, and we will after that we will add IL plus ICS. IL plus ICS is IS, so we got IS, and between IS and VS we will get theta S. Okay, this is a sending and angle between IS and VS. Okay, sending and power factor angle. Okay, so similarly we can do for T network also. Okay, so this is a charging current, this is a charging current. Okay, okay, understood. This in this way we have to do. Now let us see this one, comparison between medium and short line. Okay, medium and short line. Now here we are not doing comparison of the length between medium and short line, that we already know how is the length. Okay, for short line it is less than 80, and for medium line it is between 80 to 200. Okay, that we know, but here we are doing the comparison of performance. Okay, assuming both has the same length. Okay, after that see, this is the table that you need to keep in mind always. Okay, we know that for short transmission line, how is the short transmission R and L is connected in series. Okay, so we have sending end current is equal to receiving end current. Okay, sending end current is equal to receiving end current, and in case of medium transmission line, sending end current is less than the receiving end current due to the charging current. See, we like previously saw in case of medium transmission we have charging current in both pi and t network. Okay, so due to that reason we have is less than. Okay, so due to this is less than, here power transfer will be less, and in case of short we have full is flowing throughout the line, so here more power transfer will be there. Okay, more power transfer will be there, more power loss will happen. Okay, if more power loss will happen, then voltage drop and voltage regulation also will be more. If loss is more, then we can say that efficiency will be less. Okay, in the same way we can say for medium also, power transfer is less, therefore loss will be less, therefore voltage regulation is less and efficiency is more. Okay, and when we main comparison, like pi network is more practically used. Okay, when you talk about t network and pi network difference, pi network is more practically used due to two reasons. Okay, one is it has less node, so analysis of load flow with this pi network become easy. Okay, less node, so analysis become easy, and combination of shunt capacitor is easy with the pi network. Okay, and t network is used to analyze effect in the midpoint. Okay, effect in the midpoint of transmission line. Okay, t network is used to analyze effect of compensator. Okay, effect of compensator in the midpoint of transmission line. Now let us see equivalent pi network for long transmission line. Okay, this equivalent pi network for long transmission line we can get by comparing the ABCD parameter of both long transmission line with pi network. Okay, we can easily get this Z equivalent and Y equivalent. Okay, see this one, we already know this thing. Okay, we already know about this one. Long transmission line ABCD parameter is this one. Okay, and for pi network ABCD parameter is this one. Okay, this is the pi network. Okay, so when we will do the comparison, we can easily get Z equivalent and Y equivalent. Okay, after getting Z equivalent we will get this one. Okay, ZC sin H ZC sin H gamma L, and Y equivalent will be tan H tan H gamma L by 2 upon ZC, and ZC we know that it's a characteristic impedance. Okay, characteristic impedance is equal to root upon Z1 upon Y1. Okay, and here we need to remember for lossless. Okay, if it is a lossless line, here we can be asked to find Z equivalent. Okay, for lossless line Z equivalent is equal to root under L1 C1 into sine beta L. Okay, into sine beta L. This you have to remember. This is very important. It is asked in GATE exam. Okay, so you need to remember for lossless line Z equivalent for equivalent pi network of long transmission line. Okay, this one you need to remember, and beta is in degree. Okay, Z equivalent equals to root L1 C1 sine beta L, where beta is in degree. This we have found by, we know that for lossless line alpha is equal to 0 and beta equals to alpha equals to 0, and also see, we know that for lossless line alpha equals to 0. We will in this equation we will put alpha equals to 0, and we will put R and G equals to 0. Okay, if we put R and G equals to 0, then we will get root L1 C1, and finally we will get sine beta L. Okay, sine beta L. So this is what we have got the equation for lossless line. Okay, this you need to remember. So when we talk about lossless transmission line, we know that inductance resistance and conductance is 0. Okay, and it is an ideal case. It is not exactly 0, but it is very less. Okay, practically it is less, but ideally it is 0. Okay, here we are considering 0. Okay, so Remember that characteristic impedance, that is ZC equals to root Z1 upon Y1, and surge impedance ZS equals to root L1 C1. Okay, for lossless line, for lossless transmission line, we know that R and G is 0, and Z1 equals to R plus JXL, and Y1 equals to G plus j omega c, and this one is R plus j omega c. So R and G will be 0. So finally we will be left out with root under L1 upon C1, which is which is exactly equals to ZS. Okay, so we can say ZC equals to ZS equals to root L1 C1. Okay, so finally we will get this. Okay, this you need to remember, keep in mind this. So propagation constant denoted by gamma equals to alpha plus j beta equals to root z1 y1. When we will put r equals to g equals to 0 in this, and finally we will compare, and then we will do comparison, and then we will do comparison after doing comparison between this and this. Okay, and remember this alpha is attenuation constant, and this beta is phase shift concept or electrical wavelength. Okay, this beta, and when we will do comparison, we will get alpha is equal to 0 and beta equals to omega root L1 C1. Okay, and we know that omega is 2 pi f, and this one is v equals to velocity equals to, we know that velocity equals to 1 by root LC, and it is also equals to gamma L, where gamma is wavelength of signal, and this is frequency of signal, and this one is velocity of signal. Okay, so we can put here gamma f. Okay, so this is also equals to 2 pi f upon v. Okay, velocity. If you will put 2 pi f upon v, then it is in radian. If you will put 360 f by v, then it is degree. Okay, and similarly for total electrical wavelength, that is beta dash equals to beta L. Okay, and L is the length of transmission line. Okay, and beta dash can be written as beta value we know already. Okay, 2 pi f by gamma L we will put as it is, and into L, and 2 pi f by v is for radian, and 360 fl by v is for degree. Okay, from here you can manipulate and get these things. Okay, this is this we can do in exam also. Just we need to remember this. Okay, and this in lossless. Okay, and for lossless transmission line ABCD parameter, A equals to D equals to 1 plus YZ. Okay, upon 2. Okay, this is impedance, and this is admittance. Okay, we know very well. For lossless transmission line, we will put the value R and G value will be 0. So finally we will get after doing the calculation, we will get A equals to D equals to 1 minus beta dash square upon 2, where beta is in radian. Okay, remember that beta is in radian out here. Okay, very important to remember. And when we talk about distortionless transmission line, condition is this: L1 and L1 upon R1 equals to C1 upon G1. Okay, this one is the condition. When we will put this condition in this ZC equals to, we know that ZC equals to root Z1 upon Y1. Okay, when we will put this condition in this, then we will get a final result as this. Okay, root under R1 upon G1, and this is equals to ZD, and ZD is called impedance of distortionless transmission line, and this ZD is independent of frequency. Okay, this value is independent of frequency. So when we talk about end condenser network, we know very well how it look like. Okay, it look like this RL, and at the end capacitor is connected. Okay, this is the way. Okay, and for with load, if it is connected with load, and conductor network connected with load, then we will get positive voltage regulation, and IS will be less than IR due to charging current. Okay, this you know very well. See, this one is end condenser network. Okay, this one is end conditional network. We have like lagging load. Okay, this way we have proved by the phasor diagram. Okay, so final result is important. Okay, final result is written here. Okay, this one we need to keep in mind for end conditional network. With lagging load we have positive voltage regulation. Okay, and for no load voltage regulation is negative, and sending end current is equal to receiving end current. Okay, and current will be current is leading by Vs. Okay, and Ferranti effect. So we are sending and receiving end voltage is greater than sending end voltage. That is called Ferranti effect. We know very well. Okay, this is Ferranti effect. And during this Ferranti effect, question has come that find the receiving end voltage, and parameter of A and C is given, and they have asked to find receiving end voltage and charging current. Okay, receiving end voltage is given by VR equals to mod VR equals to mod Vs upon A, and IC equals to I per phase equals to C VRL upon root 3 ampere per phase. Okay, and this one is line voltage, and divided by root 3 we will get phase voltage. Okay, and here remember that we can either use line voltage or phase voltage, but both should be line or both should be phase. Okay, in that case we can use, and this one is very easy to remember. This one is related to ABCD parameter. Okay, so we can easily find this. See from here you can this has been proved. Okay, VR, to find VR at no load. Okay, we know this equation very well. Okay, and for no load IR will be 0. Okay, therefore VR will be Vs upon A. Okay, and so in this way we can find IS. Okay, IS is also IS and IC is same. Okay, IS and IC charging current is equal to IS. Okay, IR is 0, therefore IPH we can write. That's all. For no load we saw that we have negative voltage regulation, and we are receiving end voltage is greater than sending end voltage. That is called Ferranti effect. Because like why this happens, let's see. Because reactive power supplied by line capacitance is not fully absorbed by the line inductance. Okay, so receiving end voltage will increase and will become greater than sending end voltage. To avoid this effect, we add shunt inductor when no load or light load. Okay, to avoid this effect we use a shunt inductor when there is no load or light load, and that shunt inductor is given by this formula. Shunt inductor is equal to shunt inductance is equal to mod B upon 1 minus mod A. Okay, so due to this increase in voltage we have many problems, like there is problem of insulation failure. Okay, that's why we avoid this increase in sending end voltage. So next we have to keep in mind that among short, medium and long transmission line, there will be no Ferranti effect in short transmission line, because we know that short transmission line is RL and there is no C. Okay, because no capacitor is there, so there is no Ferranti effect in short transmission line. Ferranti effect exists only in medium and long transmission line. Okay, in medium line Ferranti effect is present. In long transmission line very high Ferranti effect is present because of long length. Okay, remember that Ferranti effect is directly proportional to square of frequency and square of length. Okay, and so there is no Ferranti effect in case of DC transmission line, because DC means frequency is 0, so Ferranti effect is not there. There is no, if frequency is 0 then there is no inductance and capacitance. Okay, so that's why this happen. Okay, now remember this condition for voltage maximum active power. Okay, how we get maximum active power. See, when we have this like system, we have vs angle delta, vr angle 0. Okay, here everything is fixed except this delta. Okay, with variation of load, delta will change, delta will only change. Okay, so we will do differentiation of this PR equation, we know very well. So we will do differentiation of this with respect to delta and put it equal to 0. Then final result we will get is load angle delta equals to beta. Okay, load angle delta equals to beta. This thing we can easily relate with alternator that we studied. There also we got load angle equals to impedance angle. Okay, and here we are getting beta, and this one there we had impedance, that's why. Okay, it is similar to that. Okay, we can easily relate. Okay, after putting this value load angle equals to beta in this, we will get this result. Okay, this is for maximum power, maximum active power. Okay, and after putting this value in q, q, we know q is what, qr is just we have to put sign out here. Okay, sign, we will get q, and if we will put this value in q, then we will get this result. Okay, and this result is negative. Okay, qr is negative. Qr is negative means what? It means transmission line will take reactive power. Okay, transmission line will take reactive power, or we can say transmission line will give leading VAR to the leading load at any voltage. Okay, this you have to remember, at any voltage it will give. Okay, transmission line will give leading VAR to leading load at any voltage. Very important point. Okay, if we connect shunt capacitor in the line, then it will give reactive power to both line as well as load. Okay, so reactive power burden on generator will decrease, so it will be able to supply more active power. Okay, so it will be able to supply maximum amount of active power. So next we will study about reactive power compensation or voltage control or power factor improvement. Okay, this we can do by do from two side. Okay, sending side and receiving side. Sending side we can only vary the excitation of generator. Okay, we can over excite the generator. If we want more reactive power, then we will over excite the generator. Okay, if we want less reactive power, then we will under excite the generator. Okay, this is what excitation. And from receiving end we can add shunt capacitor to avoid voltage regulation. Okay, shunt capacitor, shunt inductance to avoid Ferranti effect. Okay, this one is to avoid voltage regulation and also to decrease voltage regulation and also to improve power factor. Okay, and this one we add to avoid Ferranti effect. And this one we use this is synchronous phase modifier, and on load tap changing, and series capacitor. Series capacitor is used to improve the transmission of power. Okay, used to improve the transmission line capacity. And this one SPM, synchronous phase modifier, is used to under excite, over excite the synchronous generator and motor. Okay, and this one is for tap changing. Okay, so relation between main important thing that we need to remember is here is a relation between voltage and reactive power. Okay, we know for short transmission line, QR reactive power is given by VS VR upon XL cos delta minus VR square upon XL. Okay, this we know very well already. We have studied this in alternator also. Okay, this thing. So from here we can get the value of QR. Okay, by rearranging, and or we can get the value of VR equals to VS upon 2 plus root under VS square cos square delta minus 4XL QR. Okay, upon 2. This we will get. Okay, these are fixed value, these are fixed. Okay, these are fixed. Only variable is out here, QR and VR. Okay, if QR is equal to 0, if receiving and reactive power is 0, it means that demand of reactive power is equal to supply of reactive power. So voltage at receiving end equals to voltage at sending end, and it means 0 voltage regulation. Okay. If receiving and reactive power is more than 0, if receiving in reactive power is more than 0, it means that demand of reactive power is more than the supply of reactive power. Receiving end voltage will be less than the sending end voltage. It means positive voltage regulation, and this occur at peak load period. Okay. To avoid this thing, to avoid this, to make Vs equals to Vr, we have to add a shunt capacitor. We have to get this condition, we have to add shunt capacitor, or we have to use overexcited SPM, synchronous phase modifier. Okay. And third case, we have if receiving and reactive power is less than 0, it means that demand of reactive power is less than supply of reactive power. Okay. And receiving end voltage will be more than the sending end voltage. It means that it is negative voltage regulation, and this means Ferranti effect. Okay. And this occur at off load period or no load period. Okay. And to avoid this thing and get this condition, to avoid this Ferranti effect, we add shunt inductor. Okay, we add shunt inductor, or we do under excitation SPM. Okay. Synchronous phase modifier, under excited synchronous phase modifier, or on load tap changing. Okay, there are three methods: shunt inductor, under excited synchronous phase modifier, or OLTC. Now let's study about steady state maximum power transfer. Okay. That is represented by Pmax. We are already familiar with this type of diagram, like sending end voltage is given, receiving end voltage is given, and in between reactance is given. So we can easily get power flow, active power flow equals to Vs V1 V2 upon XS sine delta. Okay, this we are already familiar. Okay. So Ps equals to Vg V infinite upon total reactance into sine delta, and we know that we can make this value maximum when delta equals to 90 degree. Okay. So but this delta equals to 90 degree is not practically. Theoretically just we are studying Pmax. Okay, Pmax limit. Okay. So it is given by this. This one is very easy. Okay, case 1 is very easy. Okay. This is given, this is given, this is given, and this is given. So we can get Pmax very easily. Okay. Suppose what if this is not given. Okay, these things are not given, only this is given, only Vt is given, and these all are given, and this is given. Okay, these all are given, and only Vt is given. Theta is also not given. Then how to find Pmax? This is the main thing to understand in this. Okay. Problems are asked in the exams. Okay. So let us see. So there are certain steps to find. Okay. There are total 4 steps. Okay. In first step, what we'll do, we'll find theta. Okay. To find theta, just remember this formula. No need to think much. Okay, just remember this formula: theta equals to cos inverse this into this upon Vt into this. Okay, just remember that is cos inverse V infinite into xg upon Vt into xt plus xg plus xl. Okay. This is after getting theta, we have this voltage known, this voltage known. Okay, we have this voltage known, and this reactance is known. Okay, we can easily find the current flowing. Okay, and this same current is flowing here also. Okay, so if we get current, this current, we can easily find this voltage also, Vg angle delta, we can easily get by simple KVL. Okay, so Vg angle delta is Vt angle theta minus jxg into I that we obtained here. Okay, and after the calculation we will obtain Vg angle will be surely for 90 degree. Okay, or it will be close to 90 degree, it will be 90 or close to 90 degree, and this is a check. If you are getting this value close to 90 degree, then your calculation is right. Okay, because we are doing for maximum power, that's why. Okay, so finally we can get P max. Okay, that's all. Now let's study the procedure for designing rating of compensator for maintaining zero voltage regulation, or zero voltage regulation means receiving end voltage is equals to sending end voltage. Okay, let us see the basic things. Okay, let us see first basic things. After that we will go for the procedure. Basic thing is that if they ask to find the if they say rating of compensator means MVA or MVAR. Okay, both are same for the rating of compensator. Why is it is same? Because we know that MVA means S, and S includes P and Q both. Okay, and for compensator, that is CSH and LSH, active power is zero, always zero. Okay, so P is always zero, so only we are remaining with Q. Okay, and if it is given MVA, it means that it is MVAR. Okay, keep in mind this thing. Okay, because megawatt is always zero for compensators. Okay, rating of compensator. Okay, rating of compensator may be given as this or this. Okay, either of them, so don't get confused. Suppose we know very well that for lagging load and UPF load, voltage regulation is positive. Okay, receiving end voltage is less than sending end voltage, and for some of the leading load also receiving end voltage is less than sending end voltage. So in that case we know very well what we have to do. We have to use shunt capacitor, or we have to use over excited synchronous phase modifier. And we know that in case of leading load we might get sometime receiving end voltage equals to sending end voltage. So in that case we don't need any compensation. Okay, we don't use any compensator required. Okay, because we are already getting the valid result. Okay, so in case of leading we might get receiving end voltage is greater than sending end voltage, and this result we also get during no load and light load condition. Okay, during no load and light load condition, receiving end voltage is greater than sending end voltage. So this means Ferranti effect, and to avoid Ferranti effect we are already familiar with this, that we can use a shunt inductor, or we can do under excitation of synchronous phase modifier, so let us see the steps to find this rating of compensator. Okay, so imagine this diagram. Okay, generator, we have sending end voltage, receiving end voltage, and power is given. Okay, power PR and QR is given. Okay, and in between line we might be given XL, or we might be given with ABCD parameter. Okay, accordingly we have to use the formulas. Okay, first of all we will find the delta value. Okay, because see, PR is flowing. Okay, active power it will only flow if there is a difference of delta. Okay, it is not possible that this is VS angle 0, VR angle 0, and active power is flowing. It is impossible. There will be delta difference if active power is flowing. Okay, so according to that we can find delta value by using PR equation. find delta value using PR equation, and we know PR equation for XL is Vs VR upon XL sine delta and equals to PR. So finally we will get a value of delta. Okay, and if it is ABCD parameter, then we know very well this formula. This formula we are already aware of. With this formula, PR equals to Vs VR upon B cos beta minus delta minus A VR square upon B cos beta minus alpha. Okay, in case of ABCD parameter we have to use, or in case of XL we have to use this formula. Okay, remember this. Okay, so after getting delta, we can easily find QR value. Okay, reactive power, what reactive power at the receiving and reactive power we can get. Okay, if we get reactive power as minus sign, with minus sign, then it means that line wants to absorb reactive power. Okay, if it is positive, then it means that line wants to give reactive power. It is simple as that. Okay, so if it is negative, then QC line means reactive power that we need to give to the line is given by minus QR, and reactive power that we obtain from line for positive QR, that is minus QR. Okay, for both we have minus QR. Okay, and after that we will find out what type of reactive power demand is for load. Okay, after getting reactive power for load and for line, we can find total reactive power. Okay, total reactive power, and accordingly we have to put shunt capacitor or shunt inductor. Okay, so if overall there is demand of reactive power, if overall there is demand of reactive power, then we will put shunt capacitor, because this can only give the reactive power. And if there is overall supply of reactive power, then we will use shunt inductor. Okay, so remember one more thing about losses. Okay, for losses, Q loss equals to QS plus QC line. Okay, QC line, this one QL line or QC line. Okay, this we have to do, and we know that we know to find QS formula we know very well. Okay, QS formula is this one. Okay, this one, Vs square upon XL minus Vs VR upon XL cos delta. Okay, this one is the QS formula, and for ABCD parameter we know it will change. Okay, so this way we have to do. And remember that if the receiving end voltage and sending end voltage magnitude are equal, then Q loss sending end power equals to minus of receiving end power, and Q loss will be equals to 2QS. Okay, Q loss will be equals to 2QS. This thing you need to remember. Okay, out here. Let us see few questions to understand that concept. Okay, for reactive power demand, to find the rating of compensator. See, this one is given V1 is given 1 angle 0, and V2 is given with 1 per unit, and X is given 0.5 per unit. X is given 0.5, and here demand is given. See, this one is PS and this one is QS. QS is 0, therefore only active power, and here PR is 1 and QR is 0, so only reactive power is here also. This one is load. Okay, this one given to load, and finally you have to find QG2 means rating of compensator. Okay, so here we can easily see that active power of 1 per unit is flowing. Active power of 1 per unit will only flow in case of V1 must be leading by V2. Okay, V1 must be leading by V2, then there must be delta value. Okay, then let's find delta value. PR equals to 1 V1 V2 upon XL, sin delta 1 minus delta 2, and delta 1 is 0, therefore delta 2, so finally delta 2 we will get minus 30. Okay, it means that V1 leads V2 by 30 degree, then only there will be flow of active power from bus 1 to bus 2, otherwise there won't be flow of power. And after that we have to find QR. Okay, so to find QR we have this. Let us find QR formula we know very well. Okay, after the calculation we are getting QR as negative. Okay, we got negative QR. It means that QC line will be minus QR, means we will finally get positive. Okay, and we know that load reactive power of load is 0. Okay, so total reactive power that we give to line is 0.268. Okay, to give reactive power what we need, obviously capacitor we need. Okay, CSH we require. This is the rating of QG2 only. Okay, this is the rating of QG2. And for Q loss we know that here magnitude of VR equals to VS, so it will be 2 into QS. Okay, and QS we know very well, QS is 0.268. Okay, and into 2. Okay, for same question, if we have lagging load. Okay, if we have lagging load that is asking PR 1 per unit and QR 0.5 per unit. Okay, we already saw that transmission line was asking for 0.268 per unit, and now we have lagging load, and this will also demand for 0.5 per unit of reactive power. Okay, so we have to connect a compensator CSH compensator whose rating should be 0.5 plus 0.268. Okay, now we need to give reactive power to both transmission line and load, so total QG2 will be, okay, this we have. Okay, similarly when we see for leading load we have this type of leading load. Okay, here leading load will fulfill, see, this one will give reactive power because it is capacity. This one will give reactive power. Okay, this one will give reactive power. Suppose transmission line needs 0.268. okay, and we will subtract 0.268 from 0.4, so finally we will get 0.13. this is the excessive reactive power that is left with at the bus 2. Okay, so we have to compensate this, and this can be compensated using LSH, and whose rating will be 0.132. and for this type of leading load, here we can see that it will compensate. It will not fully compensate the line reactive power. So for to compensate fully, we have to we need to put shunt capacitor of 0.118 rating. Okay, now let's study how to control voltage, power factor and reactive power. Okay, these things we can control from two sides. One is sending end and another is receiving end. From sending end we have only one option, that we can vary the excitation. If we want more reactive power, then we will over excite the generator. If we want less reactive power, then we will under excite the generator. And from receiving end we can connect shunt capacitor, shunt inductor, series capacitor, or we can use synchronous phase modifier, or we can use on load tap changing transformer. Okay, so let us see why we want actually we want to maintain the rated voltage or voltage in the range of plus minus 5% of rated. Okay, due to these two reasons. Okay, let us see what are the reason. And suppose if we have low voltage, from here we can make out the relation between voltage and current. If P and cos theta is constant, then voltage and current have inverse relation. Okay, suppose if we have low voltage, then current will increase. If current increase, loss will increase, heating will increase, so equipments may get damaged. So we don't want low voltage. Okay, and if we have high voltage, then there will be insulation failure and equipments will get damaged. So finally, neither we want low voltage nor we want high voltage. Okay, so it should be in the range of plus minus 5% of rated. From the same formula, if we keep power and voltage constant, we have inverse relation with current and power factor. Okay, power factor, in improving power factor is the most important factor in the transmission line. Okay, see, if we increase power factor, then obviously current will get decreased. Okay, if current decrease, we have many advantages, like loss will decrease, efficiency increases, voltage regulation decreases. Okay, these things we know very well. And another most important thing is that we know that increasing power factor means what? Angle between voltage and current is decreased, that is theta. Okay, and if theta decrease, then sin theta will decrease. And we know that for reactive power, reactive power is vi sin theta. So reactive power decreases. Okay, demand of reactive power decreases means demand of complex power will decrease, so cost will also decrease. Okay, that's why we want to keep a high power factor. Okay, so these things we can control by these methods. Okay, these are the methods we can control this power factor and voltage and all. Okay, so let us study about shunt capacitor. Okay, shunt capacitor compensation. See, advantage of shunt capacitor compensation is that it will improve the power factor, it will reduce the voltage regulation or increase the power transfer capacity. Okay, or it will decrease the delta, so stability will increase. Okay, these are the advantage of using shunt capacitor. Let us suppose we have a lagging load of active power P1, reactive power Q1, and power factor Q cos theta 1. Okay, and this one is transmission line. From transmission line, QR is coming, QR reactive power is coming, and it is directly going to the load. Okay, suppose without compensator. Okay, without compensator, all the active power coming to the load. Okay, all the active power coming to the load, and we have theta 1. See, this one is the power triangle without compensator. Okay, without compensator. Suppose we want to increase the power factor. Okay, if we want to increase the power factor, then obviously this theta 1 need to be decreased. Okay, to decrease this theta 1, we have to shift this to downward. Okay, to shift this downward, what we need is we need to give reactive power to the bus, to this bus. Okay, we need to give reactive power to this bus. If we give reactive power, we can give reactive power to the bus by using the shunt capacitor. Okay, because shunt capacitor will only give reactive power. So if we connect shunt capacitor, then it will start giving reactive power. Now line and shunt capacitor both are giving reactive power. See, after connecting shunt capacitor, we have this triangle, we have this power triangle of this whole bus. Okay, overall power factor will increase. Okay, overall power factor of this bus will increase. See, theta 1 has decreased to theta 2. Okay, so power factor has improved, we can see it very well. Okay, okay, so from here we can see that shunt capacitor and line both are giving reactive power to the Q1. Okay, shunt capacitor and line both are giving reactive power to the Q1. So we can find out like how much reactive power is given to given by the capacitor. Okay, so QC equals to Q1 minus QR. Okay, this we know very well. Okay, so and here we will here all these QC QR are of three phase. Okay, so QC three phase equals to see this Q1 is what? Q1 is this one, and Q1 is this one, means it is P1 tan theta 1. Okay, P1 tan theta 1, Q1 equals to P1 tan theta 1, and QR equals to P1 tan theta 2. Okay, for this triangle QR equals to P1 tan theta 2. This we have done here. Okay, so finally we need to remember this equation. This one, this QC is, you know very well, reactive power that is given by shunt capacitor to the load, and P1 is active power input to the load. Okay, active power input to the load, and this one is the case of this theta 1 is power factor angle without capacitor, and theta 2 is power factor angle with capacitor. Okay, so in the question we may need to find input power of load by this method. Okay, output upon efficiency, or maximum power into plant load factor, or VL square upon Z cos theta 1 for star load, and 3 VL square upon Z cos theta 1 for delta load. Okay, and remember, and QC per phase, and QC per phase is what? QC per phase is per phase voltage square upon XC, and XC is 1 upon 2 pi FC. So from there we can get 2 pi F capacitor per phase into phase voltage square. Okay, and for delta capacitor we know that phase voltage equals to line voltage, and for a star we know that phase voltage equals to VL by root 3. Okay, okay. So this thing you need to keep in mind, and capacitance in each cell equals to N into capacitance per phase. Okay, this also you need to keep in mind. And for overexcited, now let us see about overexcited SPM. Okay, overexcited SPM, there is working of overexcited SPM and shunt capacitor is similar. Okay, we can easily relate, so we can easily remember. If you remember this formula, then you can also remember the formula for overexcited SPM. Okay, so only difference between shunt capacitor and overexcited SPM is that shunt capacitor will not take any type of active power. Okay, but in case of overexcited SPM, means synchronous motor, it will take active power also. Okay, and about reactive power, it depends upon what we are doing. If we are overexciting the synchronous motor, then it will give reactive power. If we are under exciting, then it will take reactive power. It depends. Okay, so we can find, similarly we can find QM, that is active power that is given by SPM. In case of overexcited, it will give reactive power. Okay, so reactive power given by SPM equals to P1 remains same whatever we studied here. Okay, active power load. Okay, and tan theta 1 is for without before connecting SPM, and P1 is same thing that we studied, and PM out here is, this is the main difference between this formula and this one. PM means active power that is taken by the synchronous phase modifier. Okay, that is synchronous machine, and only difference between this and this. Okay, so after we add SPM, overall active power will also increase. Okay, and that's why we have added this to P1, and this one is theta 2 is with SPM. We know that after before connecting SPM and after connecting SPM. Okay, means with SPM. So similarly we can find out the power factor cos tan inverse. This we will obtain from here, QM upon PM we already know. Okay, and it will be leading. Okay, overexcited synchronous motor means what? It will give reactive power, means it will give lagging current. Okay, it will give lagging current, means it will take leading current. That's why we are saying it as leading power factor. Okay, if we know about shunt capacitor, similarly we can remember for shunt inductor also. Okay, see, in case of Ferranti, let us see advantage of using shunt inductor. Okay, shunt inductor help us to remove the Ferranti effect. Okay, Ferranti effect means receiving end voltage is greater than sending end voltage. Okay, so there is insulation failure, so we want to remove that Ferranti effect. Okay. So Ferranti effect can be removed by using shunt inductor. Over voltage can be reduced. A power factor, if the power factor is leading, then we can make it to lagging also. Okay, and if we want to decrease the power factor for any reason, we can also do that. Okay, and if you have a negative voltage regulation, we can make it to positive or also to zero. Okay, and we can, if we increase the delta, then stability will decrease. Okay, remember this. And see, in this case we are putting inductor to reduce the voltage. Okay, the inductor basically takes reactive power. Okay, it will only take reactive power. Suppose before connecting inductor, QR equals to Q1. Okay, before connecting inductor, this is the power triangle. Okay, this one is the power triangle before connecting inductor. See, okay, Q1, okay, P1, and this one is S1. Okay, so this is for before connecting inductor. Okay, this one is for before connecting inductor. And after we connected inductor, inductor also started taking reactive power from the line. Okay, so overall power factor will decrease. Okay, see, angle is increasing, that's why power factor is decreasing. Okay, so this one is this triangle is after connecting inductor. Okay. So from here we can see that reactive power that is given by line equals to the reactive power taken by shunt inductor and also the load. Okay, so from here we can find out reactive power that is taken by the shunt inductor is QR minus Q1. Okay, so QL3 phase is reactive power taken by the shunt inductor, and P1 is active power input to the load, and theta 1, and this one we know that QR equals to QR equals to P1 tan theta 2. Okay, P1 tan theta 2, and Q1 equals to P1 tan theta 1. P1 tan theta 1. This we know, from here we got this formula. Okay, so and it is similar to this only. There is no much difference, and this is the case of with compensation, and this one is case of without compensation. Okay, so similarly we have QL per phase equals to per phase voltage square upon XL, and XL is 2 pi FL. Okay, this is what we got the formula from there. Okay, and similarly for under excited, and remember that under excited SPM is similar to the LSH. Okay, LSH means shunt inductor. Okay, working is same. Okay, so the formula is similar here, only difference is PM. Okay, only difference is PM. We know that it's active power that is taken by the SPM, and QM is reactive power taken by the SPM, and this one is the case of with SPM, and this one is case of without SPM. Okay, so similarly we can find out the power factor, and here we have lagging because under excited synchronous motor means it will take lagging current. Okay, it will take lagging current, that's why we have lagging power factor. And we have one special concept for no load. Suppose we don't have any load connected out here. Okay, suppose we don't have any load connected out here, and we want to increase or decrease the voltage. Okay, by connecting by connecting compensator. Okay. And we know that to increase the to increase voltage we have to put shunt capacitor, and to decrease voltage we have to put shunt inductor. Okay, that we know very well. Reactive power supplied or absorbed and is equal to new voltage. Okay, this is the receiving end voltage, that is new voltage that we want. Okay, receiving end voltage upon XL, that is transmission line reactance, into del V. Del V is change in voltage, like old voltage minus new voltage. Okay. This is the thing that this one is a very important formula. We can remember, it's a very easy. Okay. Question has been asked from this also. Okay. This one is at the no load, and only capacitor is only compensator is added. In that case we have this formula. Okay. Suppose we have this case. Okay. We have transmission line reactance is given 0.2, and old voltage is given. This one is old voltage. Okay. 400 volt is the old voltage, and we are asked to increase the voltage to 5 volt. Okay. So new voltage will be 405. Okay. So they ask in the question it will be asked that what kind of reactive power it will take or give to increase the voltage to 0.5. Okay, and that reactive power is given by Q equals to VR, that is new voltage. Okay, VR new voltage upon XL, this transmission line, and into del V, that is change in voltage. Okay, change in voltage. So this one will be what? This one will be new voltage, we know very well, that is 405 volt we want. Okay, and this one is 0.2 transmission line, and change in voltage is what? Change in voltage is just this minus this will be what? 5. Okay, this after calculating this we will get we will finally whatever the answer we will get, that is. Okay. Remember one important thing in this formula. Sometime question has been asked that suppose initial power factor was 0.8 lag. Okay, and we want to and we want to change the power factor to 0.9 lead. Okay, lead, and this one is the case of without compensator, and this one is the case of with compensator. Okay, and for lagging we took positive, that's why we will take minus theta 2 because it is the case of leading. Okay, for the case of leading we will take minus theta 2, so it will become plus. In case we have theta, in case we have to improve from power factor to 0.8 lag to 0.9 lag itself, then we don't need to change the sign. Okay, it will formula will remain as it is. And in the same way out here, if we have 0.6 leading, if we have beginning in the beginning, if we have 0.6 leading and we want to change the power factor to 0.8 leading itself, then we don't have to change this sign. Okay, no angle will change. In case we have 0.6 leading and we want to change it to 0. lagging, in that case for lagging we are taking a positive. If we are taking positive for lagging, then for leading we will take negative, and it will become plus. Okay, remember one more concept, that if we want lagging to unity or lagging to leading, in that case we will use shunt capacitor or overexcited SPM. In case of in case we want leading to unity or leading to lagging, in that case we will use shunt inductor or underexcited SPM. Now let's study online tap changing transformer. Okay, in this we have to remember only a few things. Okay, so we prefer tap changing on high voltage side due to two reasons. One is we know that high voltage side has low current, so sparking will be low, and life of transformer will increase. And another reason is that there we can obtain wide range of voltage control. Okay, so secondly, just remember this formula. Till now question has not done on this. Okay, so we'll see it later. Okay, and third thing you need to remember that sequence of control will be shunt compensation, after that online tap changing, online load tap changing, and after that we have synchronous phase modifier, and then last we will do generator excitation. Suppose we have voltage drop at receiving end. Okay, we have problems like positive voltage regulation, power factor is very low, and reactive power demand is high. Okay, and in that case what we will do, first we will try to remove this problem by putting shunt capacitor. Okay, by putting shunt capacitor at the receiving end. Okay, and if that will not work, then we will go to that online load tap changing. Okay, online load tap changing. If that also won't work, then we will go to SPM. Okay, synchronous phase modifier. If this will also not work, then we will move on to finally is generator excitation. Okay, we will increase the excitation, over excitation. Okay, and in online tap changing also we do over excitation of the synchronous motor, and here finally we have generator on only. Okay, this one is the last option. Okay, so second, let's study about series capacitor compensation. Okay, series capacitor compensation. Advantage of series capacitor compensation are it increases stability and decreases delta, and power transfer capacity increases, voltage regulation decreases. Okay, let us see how this happens. Okay, let us learn. See, for without series compensation, we have voltage drop. This one is the voltage drop for without. Okay, we have XL. Okay, and accordingly we can find out. Okay, voltage drop for this one. Okay, so accordingly we can find voltage regulation as this. Okay, if we have done series compensation, then overall reactance part will decrease. Okay, this minus this will happen. Okay, so overall reactance part will decrease, means what? Voltage drop will decrease. Okay, if voltage drop decreases, then voltage regulation will also decrease. Okay, because it is direct proportional to voltage drop is direct proportional to voltage regulation, so voltage regulation decreases. Okay, that's why we say in series voltage regulation will decrease. And for power transfer capacity, we know the formula V1 V2 sin delta upon X. If we will add capacitance in series with this inductance, then overall inductance will decrease. Okay, if this decreases, then power transfer capacity increases. Okay, this we can understand very easily. And stability, when we talk about stability, series capacitor compensated in line transfer more power at lower delta. Okay, if it will transfer same amount of power at lower delta. See, at lower delta transferring like whatever the power transferring, if it happens at lower delta, means stability of that machine will be more. Okay, let us see one example. Suppose we have this case. Okay, it is not compensated. Okay, and we have V1 V2 upon XS sin delta. Okay, sin delta, and we have to transfer power is 0.5 per unit. Okay, 0.5 per unit we have to transfer the active power, and we have V1 V2 upon X is 1. Okay, sin delta. So for this we will get delta is 30 degree. Okay, suppose after doing 50% of compensation of this transmission line. Okay, so this overall reactance part will decrease and it will become 0.5 per unit. Okay, so we have to transfer same amount of power we are transferring from the compensated transmission line. Okay, so we have 0.5 per unit power equals to v1 v2 upon x overall x will decrease. Okay, so finally we will get delta equals to 14 point. See the difference, we can easily see the difference for same power transfer, and here we have less delta and here we have more delta, and we know that less delta means more stability. Okay, so in here we have the diagram, from here we can understand more clearly. Okay, see, this one is this one we have to transfer the power, and this one is for compensated, and this one is for uncompensated. For uncompensated, maximum power is this one. Okay, 1, and for compensated we have maximum power is increased. Okay, so we can accordingly delta has also decreased. Okay, delta has decreased for compensated one. Okay, so higher stability. Okay, this way we have to learn. Now let's see surge impedance loading. Okay, surge impedance loading, SIL, that is also called as three-phase active power, three-phase maximum active power. Okay, or it is also called as ideal maximum power transfer capability of line. Okay, these are the terms that can be used in exams. Okay, so we need to keep in mind. And three-phase surge impedance loading is three-phase maximum active power transfer capacity of line to UPF loading. Okay, UPF loading means only resistance will be there, no inductance part will be there. Okay, so SIL can be derived this way. Okay, it's very simple. Okay, SIL for three-phase active power is maximum. Okay, for SIL three-phase active power is maximum, and it is we know that for active power is 3 VPH IPS cos theta, and IPS cos theta means VPH upon R. Okay, so we can do VPH square upon R, and R means out here Z, because R itself is Z out here. Okay, see, only resistance part is there, so we can write R as Z. Okay, Z. So finally we will get VL square upon root 3, VL square upon root C1 upon L1, and ZS we know that it's a surge impedance, and surge impedance is root L1 upon C1. So accordingly we got this. Okay, and it is represent and its unit is in megawatt, and in here VL is line voltage, and L1 C1 is per phase quantities. Okay, inductance and capacitance per phase quantity. See, from this diagram we can understand it more clearly. See, in here we have generator, and we have sending in voltage and receiving in voltage. Okay, suppose we have inductance and capacitance. Okay, and their reactive power are given, and they are designed in such a way that their reactive power are equal. So we can say that transmission line reactive power is compensated, so we can say it as lossless. Okay, so whatever the voltage will be here, same voltage will appear here. Okay, so VR will be equals to VS. Okay, see, reactive power is fully compensated by the line. Okay, and so line is lossless, so VS equals to VR equals to VS. So in that case, see, like in this case, the generator do not need to transfer any type of reactive power, because load is also unity, and this one has also been compensated, so generator don't need to transfer any type of reactive power. So the burden on generator has decreased, so it can transfer maximum amount of active power only. Okay, so generator has to supply maximum active power only to the UPF loading. This is the case of SIL. Okay, surge impedance loading. Now let us study, this is the most important gate point of view. Okay, effect of compensation on SIL. This was for uncompensated. Now let us do after compensating, after doing compensating. Okay, and we know the compensation are like series capacitance compensation, shunt capacitance compensation, shunt inductance compensation. These are the type of compensation, and effect of this compensation we will study on SIL. Okay, see, in this basically we have to remember this formula. Okay, this one is an impedance, surge impedance of compensated transmission line. Okay, surge impedance of compensated transmission line, SIL of compensated transmission line. Okay, surge impedance of compensated transmission line is given by surge impedance into root under 1 minus degree or percentage of series series capacitance compensation upon 1 plus degree or percentage of shunt capacitance compensation into 1 minus degree of shunt inductance compensation. Okay, this is the formula. And for SIL, accordingly we can, if we know this formula, then we can accordingly prove this formula also. Okay, we know that SIL is vs square upon ZSC. Okay, and if it is for like compensated line, then we will take surge impedance also for compensated line only. Okay, and we know the formula of this ZSC. This we will put here. After putting here, we can easily get this formula. Okay, so finally you have to remember this and this. Okay, so we can easily get this. Okay, and remember one thing, that for same amount of power transfer, delta value is different for different type of compensation. Okay, and how it is different, you need to remember that. Okay, so remember that delta value is minimum for series capacitance compensation, and after that is for shunt capacitance compensation, and after that for no compensation, and finally maximum delta will be for shunt inductance compensation. And we know if delta is minimum, then stability is more, and also the power transfer capacity is more. So accordingly we can say the order of stability and power transfer capacity. Okay, so this one is so we can say that series capacitance compensation will have more stability and more power transfer capability as compared to shunt capacitance compensation. And after that we have for no compensation, and minimum will be for shunt inductance compensation. Okay, to understand this thing, let us see one example. Suppose in exam only degree of series compensation is given. Okay, so we will consider that only in the formula. Okay, and we will put other part as 0. Okay, and this way we have to form. Suppose only shunt capacitance compensation is given, and we have to find ZSC. Okay, then we will put these two part will 0, and this only will remain. Okay, so this way we have to do in the exams. Okay, so accordingly here we have calculated the value of series capacitance compensated. If there is 30% series capacitance compensated, for this we have SIL equals to 1.19. Okay, 1.19 per unit. Okay, and for shunt we have 1.41, and for shunt inductance we have 0.83. see, accordingly we can draw the curve for that. Okay, so this blue line is the curve for no compensation. Okay, for this one is the curve of no compensation. Okay, after no compensation, we have, suppose we have SIL equals to 1 per unit. Okay, if we do compensation of shunt capacitance, then we have this curve. Okay, see, this curve has gone up. Okay, so it means that power transfer capacity is has increased, and from this delta we can say that its stability has also increased. Okay, because this delta has decreased. Okay, and for series capacitance, see, it is maximum. Okay, and here we can clearly see everything, and for shunt we have the minimum. See, accordingly we have we can say the value of delta, that this one has the minimum, and after that shunt capacitance we'll have after that. Okay, so accordingly we can decide everything. Okay, this one gives the clear picture of this shunt series and shunt inductor compensation. Okay, now let's finally study about in shunt compensation. Let's see one more a special concept that has been asked in exam. Okay, suppose loading is equal to SIL. Okay, suppose loading on the receiving end is equal to SIL of that system. Okay, in that case Vs will be equals to Vr, so no compensation is required. Okay, suppose loading is more than SIL on the receiving part. If loading is more, then obviously there will be voltage drop at the receiving end. Okay, if there is voltage drop at receiving end, it means that positive voltage regulation. And for positive voltage regulation, we know that we can remove it by adding shunt capacitor. Okay, so we have added shunt capacitor to make Vs equals to Vr. Suppose it is underloaded. Okay, means loading is less than the SIL. If loading is less than SIL, then receiving end voltage is more than the sending end voltage. It's okay. So to make it equal, what we have to do, we have to add the shunt inductor to make it equal. Okay, this we need to remember, very simple logic. Okay, logically we are saying this. Okay, and another logic we can put that suppose for loading equals to SIL, so we don't need to do anything. Okay, it's a ideal case, it's a good. Okay, so if loading is more than SIL, and we know how to increase SIL. Okay, to increase SIL we have to do series capacitance compensation or shunt capacitance compensation. Okay, so we will use that to increase the SIL to make it equal to the loading. Okay, and another, if we have loading less than SIL, and we know how to decrease the SIL. Okay, how to decrease the SIL, to decrease SIL we have to use shunt inductor. Okay, so that it can be equal. This is also the another logical point of view. Okay, so accordingly we have the gate question asked in 2016. See, inductance is given. Okay, inductance and capacitance of this 400 kV transmission line is given. Okay, and sending end voltage is 400 kV. To maintain a voltage of 400 at the receiving end also. Okay, it means that to make Vr equals to Vs. Okay, at receiving end, when the line is delivering 300 megawatt of load. Okay, now they are asking shunt compensation required is, like what type of shunt compensation will be required. So see, loading is given. Okay, to find out what type of shunt, we need to know what is the SIL, and SIL we can easily find from here. Okay, SIL formula is Vs square. Vs is given. Okay, and root under C1 upon L1. C1 and L1 is also given. So after we are getting SIL is 400, means we can clearly say that loading is less than SIL. Okay, if loading is less than SIL, we have one logic that if loading is less than SIL, then receiving end voltage will be more than the sending end voltage, means negative voltage regulation. See, to avoid this, what we will do, we'll use shunt inductor. Okay, so we have the answer shunt inductor. Okay, so another logic what we can apply is, if we have low loading as compared to SIL, to make it equal, we will decrease the SIL. We can decrease SIL by putting shunt inductor. Okay, this is also another logic. So finally we have midpoint compensation. Okay, midpoint compensation, we know this one. Okay, for no compensation we have formula PS equals to Vs square upon Vs Vr upon S X sin delta 1. Okay, for Vr equals to Vs, we will do Vs square upon X sin delta 1. So accordingly, logically we can make out formula for this also. Okay, suppose if it is at midpoint. Okay, suppose if it is at midpoint. Okay, and Vr equals to Vm. Okay, Vr equals to Vm. Okay, so accordingly we have the formula for PS equals to 2Vm square upon X sin delta 1. Okay, okay. But but condition is that this Vs should be equals to Vr, so that power is constant throughout, because this one because there won't be any active power loss due to this capacitor, okay, or inductor, okay. Only reactive power loss will be there, no. So accordingly we can design formula for this also. For an equal compensation also we can design this formula. N Vs square upon x sine delta 1 upon n, okay. Delta 1 is this, okay. So accordingly we can design. Now let's study corona. Corona is a self electrical discharge of atmospheric air. Corona, this is rho s is a surface charge density, and it is inversely proportional to the radius of conductor. Suppose if radius of conductor is more, then surface charge density will be less. If surface charge density is less, then electric field produced will be less. If electric field produced is less, then it will be less than the G, and G is dielectric strength of atmosphere, okay. G is dielectric. If an electric field produces less than a dielectric strength of atmosphere, then air molecules between the conductor don't get ionized, and so no corona effect is found, okay. If radius is less, then surface charge density is more, okay, and electric field will be more. If electric field is more and it is more than dielectric strength of atmosphere and atmospheric air, then air molecules in between the conductor will get ionized and corona will occur. So surface charge density should be smooth, okay. So the surface charge of conductor must be smooth and round to avoid corona effect. If it is rectangular, if it is rectangular, then there will be like a curve, no. If it is rectangular or triangular, then there is edges, okay, and at the edges electric field will be more, okay, because surface charge density here will be less, okay. Because surface charge density will be more, okay, and if an electric field will be more at the edges, okay. So corona effect chance will increase, okay. That's why we have to put the surface smooth and it should be round to avoid corona. In this corona topic, basically we need to remember these three formulas, okay. These three formulas we need to remember. Mostly this and this is asked, okay, in exams. So remember this formula. One is critical disruptive voltage, critical visual voltage, and corona power loss, okay. Critical disruptive voltage is a voltage at which corona is just initiated and only hissing noise is found, okay. And critical visual voltage means it's a voltage at which corona is visible with violet or blue color light, okay. So next we have corona power loss, and for critical disruptive voltage it is Vc. It is this you can see and understand. Just you have to remember, there is nothing logic here, okay, involved, okay. So remember that if Vc is power loss, corona loss will occur only when Vc is less than the operating voltage of that line, okay. Suppose operating voltage of that line is 200 kV per phase, okay. Per phase we'll see per phase value only, okay. If it is 200 kV per phase, and Vc, that is critical disruptive voltage, is 100 or 150, or it is less than 200, then corona loss will occur, okay. If it is equal to if critical disruptive voltage is greater than or equal to Vph, that is operating voltage, then corona loss will be 0. Corona loss basically depends on many factors. that is conductor's radius, distance between the conductor, air density factor, atmospheric temperature, pressure, surface irregularity, okay, and dielectric strength of atmosphere. So on these things, corona loss depends, okay, and critical disruptive voltage depends on these all factors, okay. Suppose if critical disruptive voltage is 100 and we are operating at 50 kV, then obviously why corona loss will occur? Because minimum voltage required for corona is 100, okay. Suppose we have 100, so corona loss will not occur below 100. That's why we have these conditions, okay. If we see find suppose we are asked to find power loss, corona power loss, first of all we will find Vc, okay. Vc, and if Vc is less than Vph, then only we will find the power loss, okay. Otherwise we will not find, because otherwise the power loss will be zero only, okay. That's why. And let us see effect of an effect of corona, or factor influencing corona, or method to reduce the corona, okay. One important thing that you need to remember, only advantage of corona is that it reduces the stiffness of lightning surge, okay. How it reduces the stiffness of lightning surge, let us see. Suppose Vc, that is critical disruptive voltage, is 163 kV, okay. After seeing all those factors, environmental factor and all, everything, we found that Vc is 163 kV, okay. And lightning is obviously suppose if lightning is of 500 kV, means per phase voltage of that line will be more, okay. More means it will be so high that it will be more than this critical disruptive voltage. So if it is more, then corona loss will be more, okay. Then corona loss will be more. Due to this corona loss, stiffness of lightning surge will reduce. Remember that corona loss is directly proportional to frequency plus 25, okay. Frequency plus 25, and it is inversely proportional to critical disruptive voltage. If critical disruptive voltage is less, then corona will be less. If it is more, then corona will, if critical disruptive voltage is less, then corona will be more. If critical disruptive voltage is more, then corona will be less, okay. So you can find from here, or from the formula. If you remember the formula, then you can remember that thing also, how power loss is related. See, out here we can see it is directly proportional, okay. And critical disruptive voltage is directly proportional to m naught r. And m naught is what? M naught is surface irregularity, r is radius. For this to improve this factor, we will use hollow conductor, okay. Hollow conductor have more m naught. See, hollow conductor have more m naught, and r of hollow conductor is also more, okay. Effective radius is also more. And b is what? Temperature, okay. From here you can find, okay. See, delta B is above, okay. So it is directly proportional to the pressure, okay, and inversely proportional to the temperature. From here you can find out relation. If you remember the formula, then you can remember these relations also. Now let's study overhead line insulator. Overhead line insulator, insulator are of total 6 types, okay. Let us see one by one. One is pin insulator, okay. Pin insulator is used up to 33 kV. So it is used in distribution line. Suspension insulator is used between 33 to 1200 kV, and material used are ceramic or glass or silicone, okay. And strain insulator is used to increase the tension, and if we increase the tension, means sag is decreased. So we can say strain insulator is used to decrease the sag, in case of road crossing, river crossing, railway, dead end of tower. Okay, and spool insulator is used up to 11 kV, and stray insulator is used up to 400 kV. Basically it is used to support the towers. Okay, and post insulator is used in current transformer, potential transformer, circuit breaker, or isolator. And remember one point that insulator strength depend upon switching over voltages. Basically most important among all these type of insulator is suspension insulator, because numerical type of question are framed from this topic only. Okay, so let us study this. You have seen the transmission line, that there are different number of disc in different kind of transmission line. Why is it so? Is it so because it is so because there are different level of voltages. Okay, and number of disc varies with variation of voltages. If voltage is more, then number of disc, insulator disc will be more. Okay, and this number of disc, by seeing the number of disc, we can decide like how much voltage that transmission line is carrying. Okay, by this formula, number of insulator disc operating phase voltage, that is N equals to operating phase voltage upon maximum withstand voltage of each disc, that is generally 11 kV only. Okay, generally we take it 11 kV for each disc, withstand voltage is 11 kV. Remember this. Okay, suppose we can count the number of disc easily from outside, and if we multiply it with 11, then we will get the operating phase voltage. Okay, so it is very easy to use. Now we have string efficiency. String efficiency is basically given by operating phase voltage upon N into voltage of disc nearest to that conductor, and N is the number of disc. Okay, and suppose for N number of disc, it will be V1 plus V2 plus V3 plus Vn upon N into Vn. Okay, and VPH always, phase voltage always will be equal to the sum of all the voltages along the insulators. Okay, sum of all the voltages along all the insulator will be equals to the phase voltage. Okay, and remember one thing. Suppose similarly for an N disc we found, suppose we have 3 disc. For that formula will become V1 plus V2 plus V3 upon 3 into V3. And remember one thing, that if voltages along if voltage across all the disc is same, that is V1 equals to V2 equals to V3, then the efficiency will be maximum. When we study about this efficiency of these insulators, we come across 3 type of capacitance. Okay, one is link to link capacitance, another is link to ground capacitance, this one is link to ground capacitance, and third one is link to line capacitance. Okay, link to line capacitance, third one. Okay, like when we consider when we find a string efficiency considering only these two, only CS and CM, in that case, that is the case 1. Okay, that is case 1. If we consider all the capacitances, all 3 types of capacitances, then that is case 2. We will basically remember, we will focus more on case 1 because this one is very important for exam point of view. This one is not that important, but also its formula is easy, so we can remember it. And we will study only for 3 disc system. Okay, 3 disc system only we will study for both case 1 and case 2. I will just remember the formula. we won't do any type of derivation in this. Let us see for case 1. This case 1 is formula for 3 disk for 3 disk without cx and cy. Suppose you are given with the value of k, and k is nothing but the ratio of cm and cs. And remember that cs value is always will be always greater than cm, so k value will always be less than 1. Okay, and suppose k value is given and we are asked to find a string efficiency. We can easily find a string efficiency just with the value of k, okay, by using this formula. Okay, by using this formula, can find the efficiency of k. This formula is nothing but came from this formula only. After seeing the circuit, we will find v2 and v3. Okay, we will find v2 and v3. See, from here we can find v2 and v3. This way we will find. Okay, we will find v2 equals to v1 into 1 plus k, v3 equals to k square plus 3k plus 1 into v1. Okay, and we know the efficiency equals to v1 plus v2 plus v3 upon 3 into v3. Same thing we have done. See, v3 is this only, and v1 got cancelled, and v1 plus v2 plus v3. So finally we get string efficiency equals to k square plus 4k plus 3 upon 3 into k square plus 3k plus 1 into 100. And basically remember this. Okay, value of v2, because sometime question is asked, find the value of find the voltage across find the voltage across capacitor 2 by voltage across capacitor 3. In that case we can find. Okay, and from this we can find the efficiency by putting in this formula. Okay, so remember this only basically. So when we consider when we consider all the capacitance, then we have this formula. If voltage, all the voltages across the capacitance is given, then we can easily find efficiency 1 by 3 into v1 upon v3 plus v2 upon v3 plus 1 into 100. That's all. This is so easy to find. Okay, let us see about this. Okay, guarding. Okay, guarding, due to this guarding, what happens is, due to this guarding, ix equals to i1 and iy equals to i1 and ix equals to i2. Okay, if this happens, if this condition happens, then voltage across all the capacitance will be same, that is v1 equals to v2 equals to v3. And if this happen, then we know that efficiency will be 100%. Okay, so with the help of guarding we can increase the efficiency, or we can increase the efficiency to 100%. Okay, and when we if and another and keep in mind this formula, relation between cx and cm and cy and cm from here. Okay, if efficiency is 100%, then link to line capacitance of pth link. Okay, link to line capacitance is this. Okay, relation between this and this we can find. Okay, relation between this and this we can find by using this formula. Suppose p equals to 1. Okay, for 1 p1 we'll put here 1, and cm upon 3 is number of disk, 3 minus 1. So we will get cp equals to cy equals to so cy equals to cm by 2. Okay, it means that iy equals to i2 and v2 equals to v1. Okay, and suppose for point 2 cp equals to cx equals to 2 into cm upon 3 minus 2 equals to therefore cx equals to 2 cm. Okay, so these things, so all the voltages will become equal and efficiency will become maximum. If this happens, then efficiency will become maximum, because this condition occur after satisfying this. Okay, so efficiency will be maximum. Now, what are the advantages of having maximum string efficiency or efficiency equals to 100%? Okay, if we have maximum efficiency, then more transmission line voltage will increase. If transmission line voltage increase, then surge impedance loading will increase. Surge impedance loading, we know that it's a maximum 3-phase active power. Okay, therefore power transfer capacity of that line will increase. These are the advantages. Okay, and also one another advantage is that voltage across all the capacitance will become equal, and stress on all the insulator will be same. Okay, so stress is distributed in that case, so a long life of the insulator will be there. Okay, so to improve string efficiency, these three are the method. Okay, these three are method. Okay, first one is gartering. This one is basically practical method that we already saw how this work. Okay, this is the way how it work. So increase cross arm length. If we increase the cross arm length, then the string efficiency will increase, but this is not practically used because tower will become very heavy if you will put bigger length. Okay, bigger cross arm length. And non-uniform disc is also not practical because maintenance issue is there. If there will be different size of insulators, then it's very difficult to do maintenance. Okay, so we do not prefer these two method. Okay, these two method, we only go for this method. Okay, this is only to study. Practically it is not used. So remember these things that you will always see in the transmission line. This one is arcing horn. Okay, arcing horn is basically used to protect insulator from lightning surge. Okay, and this one is gartering. This we know very well how it works. It is used to increase the efficiency, string efficiency. And vibration damper is used to damp out the vibration due to wind. Okay, and insulator strength depend on switching over voltages. This point you need to remember. This is asked in exam. Okay, GATE exam, this one better remember. Now let's study distribution system. Distribution system are basically of two types. One is AC and DC. Okay, AC is used for a public utility, and DC is used in like industry substation, generating substation, generating station. And DC is also used in a protection system. Whatever the protecting equipments we use, that operate basically on DC. And DC is used, we know that DC is used for like high voltage transmission line. When we have to transmit power for longer distance, in that case we use DC. Okay, so let us understand what is feeder, distribution, and service mains. Feeder is a line between which no tappings can be taken, and this line is basically between the substations. Okay, so between that we cannot take tappings for a utility purpose. And distributor is a line between which we can take tappings. Okay, distributor is a line that is near to our house, from where we take tappings using power cables. Okay, that is distributor line. And service mains is a cable that connect houses to the distribution line. Okay, that's all. So mainly we have to study different type of system, that is radial system, source from both end, and ring system. Okay, radial system is nothing but a source from one side. Okay, source from one side, source from two side, and ring system. Let us suppose source from one side as type 2 system. Type 3 is source from both side, and type 1 is source from one side, type 2 is source from both side, and type 3 is ring system. There is no big difference between radial type 1, type 2, type 3. Only difference is, see, in case of radial system, we will have source in only one end of the transmission line. In case of type 2, we will have source in the both end of a transmission line. We can see both end. We are giving for radial we are giving only 220 here, and for this both end we are giving 220 and 215. Okay, and for radial, and if we connect this both hand, no, A and E, then it will become a radial system. There is nothing much we have to do. Okay, and if we connect this A and E, it will become a ring, and it will become a ring system. It will become type 3. Okay, if we connect this 2 point, if we connect these 2 point, it will become a type 3 system, that is ring system. Okay, only difference is that. Basically, difference, a big difference come when we do analysis. Okay, when we do analysis, when we see, suppose we are given with voltage, load current, and the resistance between all the lines. Okay, voltage, load current, and resistance. Okay, voltage, load current, and resistances. Voltage, load current, and resistances. Okay, suppose these are given, and finally we have to do calculation and find the voltage at each node. Okay, after doing calculation, we have found this calculation, this is for a same circuit. Okay, we have considered the same circuit for all this system, so that we can compare it very easily and know the differences between them. Okay, after doing calculation, we have found these voltages. Okay, these voltages, see, we can easily find out the difference, that this one, when we talk about radial system, at far end of the generating station, voltage is decreasing. Okay, voltage is decreased at very large level. And when we talk about this both hand system, voltage has decreased, but not like radial. And ring voltage is very much better than these two. So accordingly we can make out that voltage of this system is very bad, voltage level of this system is very bad. This one is little bit good, and this one is best than both of these. Okay, and when we talk about reliability, power reliability, suppose there is power cut out here, so any of the consumer will not receive any amount of power, so power reliability is very bad of this radial. And if suppose if there is power cut out at this place, then the consumers can receive power from this end. Okay, so it is a little bit better than radial. And when you talk about ring, it is best. Okay, and when you talk about power loss, here only one line is there, so power loss will be less. Here also power loss will be less, but when we talk about ring system, here power loss is more, because there are several lines connected. This one is this radial system, like only advantage is that power loss is less, and another advantage that it is used as load frequency control, and these two cannot be used for load frequency control. Okay, these are the advantages of radial and disadvantages. And when we talk about calculation and see, when we talk about this ring system, here also we have minimum voltage at node C. Okay, to avoid this minimum voltage at node C, we will do a proper interconnection between node A and node C. We will connect a we will connect a line between transmission a line between A and C, whose resistance should be less than least resistance of parallel path. Okay, see, suppose we have connected the line whose resistance is RC. This RC should be less than this least resistance. Which one is least resistance? This one is least resistance. This is 0.4. So RC should be less than 0.4. so that we can get better voltage at this level at point C. So finally we can decide that ring system with proper interconnection is the best to avoid low voltage and low power reliability. So we have till now we have understood the differences between all three types, okay, and how to improve voltage level in type 3 also by doing interconnection. This we have understood. Now let us see the calculation part, that is very important for gate exam and engineering services. Mainly calculation part come from type 2 and type 3. This one is very easy. We can solve it by simple KVL and KCL. See, if we are given this load current, this one we can see that this one is open, so this one will be 0, so this one will be 12 ampere, and resistance is this, and here we have 27 ampere by adding these two, and we have resistance this resistance and current also we can find, okay. So finally we can easily get the node voltages of all just by KVL equation. Mainly we have to learn to calculate these, okay. And here also procedure are same for both of these, type 2 and type 3. Only difference come when we do like VA minus VE equals to, there will be some voltage drop, okay, but here VA minus VE we have connected, so there will be 0. So VA minus VE will be 0 for this, and VA minus VE will be some value for this. Only difference is that, okay, during calculation. Now let's see the calculation part. Let's see the procedure to solve type 2 and type 3. First of all, assume A from VA, then calculate IA using this one, okay, this equation. This you can do very easily, and substitute IA in each of these, okay, each of these, and check for sign change, and the node having sign change will have the minimum potential, okay. And after that, after getting IA current of each node, and resistance is already known, so by applying KVL we can easily find potential of each node. Now let us see few examples to understand it better. Let us find the node voltages of this type 2 system. Both hand source is present, okay, and first of all, steps are, first of all, assume IA from VA. We have IA, okay, IA we took. After that this one will be IA minus 10, this one will be IA minus 25, this one will be IA minus 37. After getting this, now we will we know that voltage drop between this will be VA minus VE. So VA minus VE will be what? VA minus VE will be equals to voltage drop across this line, okay. So we know that we already know IA into resistance, this IA into resistance, this IA into resistance. When we'll add all this, that will be total voltage drop equals to VA minus VE. So that's what we have done here. VA minus VE, it will be 5, so this one be equals to this voltage drop, plus this voltage drop plus this voltage drop. So after that we can get equation, we got 26 ampere, okay. After getting 26, we will put this we will put this 26 in this, we will get 26. When we put 26 in this, we will get 16, so we will get 10 ampere, and here we are getting minus 11 ampere. And we know that wherever we will have sign change, that node will have minimum potential. So point D will have the minimum potential, okay. So we got the minimum potential point. Now we can easily find the voltage at each node, because current and resistance are known, known, so we can easily find potential at each point, okay. So check sign change occur on point D, so it will have so that is the minimum potential point, and VB equals to this minus this drop, okay. This one we got, okay. So VC will be this potential minus this drop. See, same thing. In this way we can find all. Okay, suppose we have ring system for this same, we just have to connect this point and this point. In ring system, this part will become 0. Okay, VA minus VE will be 0 because we have connected now. That's why. Only difference is that, and the procedure remains the same. See, here we can see the calculation of ring system. Procedure is same, only difference is out here will come 0, and after that we will get IA and put this value in all these. Okay, and wherever we will have first sign change, here we have the first change at C. Okay, so C will have the minimum potential, and after getting these IA and resistance, we can easily find voltage drop or all. Okay, now let us see how to calculate if we have interconnection. Okay, if we have interconnection, that is RC, if we connect interconnection to improve the voltage level. See, let us see. Procedure remains the same. First of all, we will remove the RC part. Okay, first of all we will remove the RC, and we will calculate voltage across voltage at point C. If we know voltage at point C, we can find VTH will be 220 minus 214.6. After getting VTH, we will find RTH will be this both are the parallel path. When we add this both parallel path, we will get 0.24 as RTH, and after getting RTH, VTH, and we have already RC, so we will get IC we got. Okay, after getting IC, after getting this IC and this resistance and current is known, so means voltage drop across this is known, and voltage across, now we will assume this one IA, so this one will become IA minus 10. Okay, IA minus 10, sorry, IA dash and IA dash minus 10. After doing that, we will take this loop. Okay, after solving this loop, we can get IA dash we can get. After getting IA dash, we will now we will calculate the voltage drop. Okay, so IA dash 220 minus IA dash into this, we will get this node voltage, and after that this node voltage minus this drop, we will get this node voltage. After getting this node voltage and this current, we know this is IC 10.38, and this one is 4.77. okay, coming from here, and this one is going. So when we will do minus, we will get minus 0.167, and into this we will get voltage drop of this. So finally, that's all we have to do in this chapter. So these are the gate questions, and this is also one gate question asked. Okay, you can see this. Now let's study power cables. In power cables, first of all we will study about parameters of the power cable, and next we will study about dielectric power loss. Next, to find per phase capacitance in 3-phase power cable, and finally we will study about electric field stress or voltage gradient in power cable. Okay, these things we have to study in power cable. Let us start from parameters of power cable. Parameter of power cable consist of conductor of resistance, resistance of conductor, resistance of insulator, and capacitance of insulator. Resistance of conductor we know very well. For a copper, we know that it is rho L by A. Okay, rho L by A. Here rho C is the resistivity of conductor, and L is the length of cable, and pi r square is the area of this conductor. Okay, and for insulator, resistance of insulator is rho I upon rho I upon 2 pi L ln capital R upon small r. Here capital R is the radius of overall cable, and small r is the radius of conductor. Okay, radius of conductor. And rho I is the resistivity of this insulator. Okay, so you have to remember this formula. Remember this formula of capacitance, of this capacitance and resistance. Okay, for insulator. And for capacitance of insulator, we have Ci equals to 2 pi epsilon naught epsilon r upon ln capital R upon small r farad per meter. And if we know capacitance, we can easily find resistance, because we can easily find charging current, that is IC. Okay, this one is IC. Okay, IC. This one is IC, and this one is IL, leakage current across resistance. So IC, we have IC here. So IC means V upon XC, and V upon XC means 1 upon omega C, and finally we will get 2 pi FCI and VPH. Here voltage we will take always per phase voltage. Okay, because in here we are calculating for phase, that's why we will take per phase, and it will be ampere per phase. And one more thing you need to remember, that relation of length and resistance, relation of length and resistance in conductor and insulator. From the formula we can easily say resistance of a conductor is directly proportional to length, and resistance of insulator is inversely proportional to length. Okay, so you need to remember, because question has been asked. Okay, so logically also we can do that. For copper, for conductor, its resistance per unit length gets added in series, that's why its overall resistance increases with length. And when we talk about insulator, its resistance per unit length get added in parallel, that's why its overall resistance decreases with increasing length. Here see, it is added in parallel, and this one will be added in series. Okay, this is the logic. And for HVAC, you know that there is frequency of 50 Hz, that's why there will be charging current, that is due to capacitance. Charging current will be there, that's why we cannot use HVAC cable for more than 40 kilometer. But in case of HVDC, there is no such frequency, so there is no charging current, so we can use this for length more than 40 kilometers. And remember this parameters. Okay, this small r is radius of core radius, and capital R is radius of cable, T is the thickness of this cable. Okay, capital R minus small r, and IL is leakage current, IC is charging current, leakage current, charging current. Okay, so that's all we have to remember. Main thing is this formula. Okay, insulator resistance and capacitor capacitance of insulation, these two you need to remember. Okay, so next let's study about this dielectric power loss of cable. See, dielectric power loss basically happens due to insulator resistance and capacitance of insulator. Okay, due to Ri and Ci, power loss happens in the cable. And finally you need to remember a formula. See, power loss means what? It will be across resistor. Okay, resistor. So power loss will be Vph square upon Ri. Okay, per phase voltage square upon Ri, and Ri we will get from here. Okay, from here, see, from this triangle, from this phasor diagram we can easily understand this phasor diagram. This IL, leakage current, will be in phase with voltage, because this leakage current is across resistance, and this capacitance IC, that is charging current, will be leading by phase voltage. Okay, because this is purely capacitor. Okay, that's why. So finally we will get total current. It will form angle delta with IC, so tan delta will be this upon this. Okay, IL upon IC, tan delta. So we know that IL is Vs upon Vs upon Ri, and IC is Vs upon xc. Okay, so finally we will get 1 upon 10 delta equals to 1 upon ci ri. Okay, so ri we will get from here. Okay, ri will be so after getting ri from here we will put in this equation. So finally we will get power loss equation as vph square omega ci and 10 delta. Okay, 10 delta, and this 10 delta is also called dielectric loss tangent or dissipation factor. Okay, this thing this one is very important equation. It question has been asked related to this. Okay, power loss equals to vph square omega ci into 10 delta. Remember this. And next we need to remember about to find capacitance per phase of a 3-phase cable. Okay, capacitance per phase, you just remember this thing. Okay, capacitance per phase cable means 3ca plus cb. Here 3ca plus cb, where 3ca plus cb equals to 9 c2 minus c1 upon 6, or equals to 2 cpp. Okay, and ca means capacitance between phase to phase. cb is phase to slate capacitance, and c1 is capacitance measured when all 3-phase conductor are sorted, and c2 is capacitance measured with 2 conductor bunched and sorted. Okay, and cpp is capacitance between any 2 phase when 3rd phase is sorted. And next, at last, we have to study about electric field stress or voltage gradient of power cable. See, basically conductor, above the conductor there is insulator. Okay, and layer of insulator that is close to the conductor has maximum electric field, and the insulator surface, outermost surface, has the minimum electric field. Okay, electric field, due to this variation of electric field across the insulator, there is potential gradient. Okay, voltage gradient is there. Okay, due to this variation of electric field, due to this potential gradient, leakage current will flow in the insulator, and due to this leakage current there is I square R loss. Due to this I square R loss, there is heating effect in the cable. Okay, and due to this heating effect, cable may get damaged. So to avoid this, we go for different methods to reduce this. Okay, we have like first method is most economical size of cable, that is given by capital R equals to 2.718 R. Okay, and grading of cable. Second method is grading of cable. Grading of cable basically means maintaining same electric field throughout the cable. Okay, so grading of cable are of 2 types. One is capacitance grading and one is interslath grading. Interslath grading requires transformer, and so it become very costly, and this one is not practically used. Okay, interslath grading. Practically used method is capacitance grading, and this most economical size of cable, that is capital R equals to 2.718 R. Okay, so capacitance in capacitance grading, you need to remember is that this is a practically used, and by using in this grading we use different insulation of different epsilon R and for different length. Okay, for different length we use this insulator of different types. Okay, so formula is given by V equals to EH1 R ln. This EH1 is nothing but it's electric field. Okay, it's a electric field, high electric field. Okay, EH1 means EH1 R ln R1 upon R, EH2 R1 ln R2 upon R1, EH3 R2 ln capital R upon R2. Okay. So remember this one also, equation of electric field and voltage. Okay. Electric field is q upon 2 pi epsilon naught, and x is the distance between charge charge conductor and length outside the conductor. Okay, and q is the charge on that conductor, and v equals to q upon, after doing integration and all, we will get v equals to q upon epsilon naught epsilon r ln capital R upon small r, and finally we can write v equals to e. Okay, this one we will take at ex ln capital R upon small r. This one is the most important. Okay, this one is voltage, this one is electric field, and x is distance from center of conductor to any point on insulator. Okay, x is that, and ln capital R we already know is the radius of cable, and small r is the radius of conductor. See, to avoid this heating effect, to avoid this potential gradient, we can also use insulator of higher epsilon r. Okay, but insulator of higher epsilon r are very costly. That's why we to avoid this problem, we go for these methods. Okay, there are 1, 2, 3 methods are there. Okay, and among this interslith grading is not practically used, this one is practically used. So remember the formula of this one, may be asked in exam. Okay, and remember this most economical size of cable. Okay, so this is the thing that you need to remember. Let us see the actual note. This one is for electrical field stress voltage gradient. Okay, in this way we have proved. Okay, so this one is, see, electric field is maximum at the near the conductor, and it decreases on the surface of insulator. Okay, this way, after using economical size of cable, this one will be the gradient. Okay, this one will be the curve. Okay, so next we have this one. Okay, see this one, and this one is the method for, this one is interslith grading. Okay, this one is the method for interslith grading. We are using transformer, and we will give different voltages. Okay, so that we can make it. And this one is a ideal grading. Okay, this one ideal grading, this is not possible actually. This one is for 3-phase cables, practical measurement of CB, CA, CB and CPH is this one. Okay, finding C1 and finding C2. Another way we will find C2 also. Okay, C2 we will find this way. Okay, now let's study load frequency control. Load frequency control is very much required because due to these following reason. Okay, because decrease in frequency will cause saturation in load, and increase in frequency will cause hysteresis loss, and turbine may get damage, and also speed of motor will change with varying of load, and unwanted operation of relay, because CT and PT get affected by the variation of frequency. Okay, due to this reason we required load frequency control. And method of load frequency control are most important method is speed governing valve control, and peak load plant, and load regulation. Okay, so let's study speed governing valve control. See, speed governing valve control is basically suppose any plant is operating at normal load. Okay, if we suddenly increase load. Okay, if we suddenly increase load means machine will lose its kinetic energy, and its speed will decrease, and if its speed decrease, then its frequency will decrease. Okay, to bring back the machine at the rated speed and rated frequency, we will open the valve. If we open the valve, then steam input will get increased to the turbine. Okay, if steam input increase, then the turbine will rotate more fastly, and speed of that generator will be maintained. And if speed of generator is maintained at rated, then we will get, then machine will accelerate, and we will then frequency will increase, and we'll get nearly to rated frequency. Okay, ideally rated frequency, frequency is plus minus 1% of 50 hertz, and practically it is plus minus 3% of 50 hertz. Okay, and similarly, when you have when the load will decrease, if load decrease means machine stores kinetic energy. If machine will store kinetic energy, then speed will increase. If speed increase, then frequency will increase. Okay, so in that case, to maintain the rated speed and rated frequency, we will start closing the valve. Okay, if we start closing the valve, then steam input will decrease. If steam input decreases, then machine will decelerate. If machine decelerate, then frequency will decrease, and we will try to bring near to the rated frequency. Okay, in this way we will use the governing valve. Okay, so in this topic, you need to remember some formula, very basic formulas are there. Okay, this formula, and this formula you need to remember. Okay, all this formula you need to remember. If you remember sequentially, then you can remember all. Okay, let us see. If line trips, okay, load loss, trip of transmission line happens. If trip of transmission line happens, and if addition of load is demand, okay, if the load is added, okay, in that case how the frequency will change, that we will see. Okay, see, Fn is new frequency, and this Fi is initial frequency, and here H is inertia constant, S is MVA rating of generator. This one is H is inertia constant of generator, and del PD is changing load. Changing load might be positive or negative. Okay, so and TD is time delay. See, this time delay is basically due to what? Because see, so if we have increased the load, okay, so if we have increased the load, then frequency will decrease. After that the feedback system will work, and then valve will open. After that it will take some time. Okay, so some transition time is there to maintain the frequency to rate it again. Okay, to come to the original position, it will take some time, so that time is time delay. Okay, so to understand this formula, understand like this, that see, if the machine is not loaded, okay, if the machine is loaded and working normally, okay, at frequency near to 50 hertz, means initial frequency. See, frequency will always depend on the kinetic energy of the machine. Okay, frequency is directly proportional to the root of kinetic energy. Remember that. Okay, frequency is directly proportional to the root of kinetic energy, and kinetic energy of machine under undisturbed condition is what? Under undisturbed condition, kinetic energy is H into S, that is an inertia constant into MVA rating. Okay, this one is the initial kinetic energy. Suppose if load is trip, here we are saying tripping of transmission. If load trip, then what will happen? Kinetic energy of the machine will increase. Okay, that's why we have done for new frequency. Similarly, new frequency will be proportional to the an old kinetic energy plus new kinetic energy. New kinetic energy is del PD plus ID. Okay, time delay. Okay, del PD plus time delay. Similarly, we can understand for addition of load also. If we add load, then kinetic energy will decrease. Okay, that's why we have for new frequency, kinetic energy is decreasing. Okay, from this existing kinetic energy, this del PD into TD is decreasing. Okay, This is the logic to remember this formula. Okay, and remember this del f means steady state frequency. Okay, after changing load, there will be change in frequency also. Okay, and if we increase the load, then frequency will decrease. Okay, means del pd will be negative. Okay, and if we decrease the load, then frequency will be increasing and del pd will be positive. In that way, we have steady state frequency equals to new frequency minus old frequency. Okay, and it is negative of, and this one we will after understanding these things, we will use this formula also. we can find a steady state frequency if change in load is given and b and r value is given, and b means speed regulation parameter and damping coefficient. Okay, and b means damping coefficient and r means speed regulation parameter. Okay, if these two parameters are given and change in load is given, in that case we can find steady state frequency. Okay, steady state frequency deviation we can find in that case. Okay, and changing load, if load is removed, means load loss, means it is subtracted, load is subtracted. Okay, then we will take minus del pd. If we take minus del pd, then it will become minus plus. Okay, so in case of if load is added, then we will take plus del pd. Here we will take plus del pd, then it will remain as it is minus only. Okay, so this thing you need to keep in mind. Okay, sometimes question has been asked this way. Okay, it is not in gate, but it is important for ESC exam and all. Maybe it might come in gate also. Okay, it is very easy to remember, so better remember it. Okay, so let us see speed regulation parameter. Speed regulation parameter is nothing, just suppose rating of a machine is given 100 MVA and like 50 Hz. Okay, and like what does that means? Means at if machine will give 100 megawatt, if machine is operating at 100 MVA, then that frequency then the frequency will be 50 Hz. It means that. Okay, but what if machine is not at 100 MVA, machine is at 0 MVA? Okay, means machine is at no load. At that time frequency won't be 50 only, it will be 52. Okay, suppose it is 52, but generally it will be more than 50. Okay, suppose here we are considering 52 to understand the things better. Okay, suppose we are considering 52. Okay, at no load machine is at machine frequency is 52, and at full load machine frequency is 50. Okay, so we can find del f. Okay, change in frequency is what? Change in frequency we can see that 52. Okay, 52 means 2. Okay, so 2 we will keep here. Okay, del f, and change of load is what? Change of load is from 0 to 100. Okay, so we will take 100. So finally we will get minus 0.02 Hertz per megawatt. Okay, so R is del f upon del p Hertz per megawatt, and minus sign is for negative. See, you can see negative slope, that's why we have taken minus sign. Okay, and after getting this value means what? This value means with 1 megawatt increase in load, frequency of that machine will decrease by 0.02 hertz. Okay, it means this. Okay, so it is very important thing, and this can be written in per unit also. You only think per unit is what? No, actual value upon base value. Okay, so del f upon f rated and del p upon f rated. So after rearranging we will get R into this into S upon F rated. Okay, so this we have. Okay, and if after converting this into RPU, we will get 0.04, and this can be also written as 4% droop. Okay, in the question sometime it is given 4% droop. Okay, it means this only. Okay, remember this very important thing. And if we are given old R per unit, okay, old R per unit and old base is given, okay, and we want to convert it into new, then we have to use this logic, okay. This logic is similar to X per unit. We used to find reactance, no, like X new equals to X old into S new upon S old into V. There was voltage also, okay, V old upon V square, okay, but here voltage is not here, okay. So it is similar to that. And logic to find B is just opposite of this, means it is similar to H constant, okay, like inertia constant, like new equals to old into BPU new equals to BPU old into S old upon S new, okay. It is that, okay. And B is damping coefficient. Let us finish this first, okay. This we understood. After that, see, if many generators are connected in parallel, then we want to find R, okay, means speed regulation of that parameter, okay. First we will take all the R in a common base, okay. That's why we have written like 1 upon R equivalent equals to 1 upon R1 and 1 upon R2, and all the machines R will be taken on a common base, okay, common MVA base, okay. So that's why we in here it is new, okay, means it is taken into common base, so you have new. And remember that if in the question it is given that governing valve is blocked, means always R is infinite, okay. Remember this, governing valve is blocked means R is infinite. And let us understand this damping coefficient. Damping coefficient is nothing, just a 1 upon Kp, okay. It is del Pd upon del F, okay. Just reverse of this only, okay, just reverse of this speed regulation parameter. It is del Pd upon del F, that is change in percent change in load into total load upon percent change in frequency into rated frequency, and this unit is megawatt per hertz, okay. And similarly we can find per unit also, B into F rated upon S. C is just opposite of this only. See, here is S upon F rated, here F rated upon S, okay, and this one is also opposite to this, okay. So remember this is very easy to remember, okay. And remember one most important logic, many questions has been asked, just by seeing you can answer it, okay. Suppose many generators are connected and sharing a common load, okay. Many generators are connected sharing a common load, and all the generators have different R, okay, different droop characteristic. All the generators have different droop characteristic, okay. So in that case, if load is increased, then they will ask that which generator will have the maximum loading, okay. This we can easily say, just see which has the lowest droop characteristic, okay. And remember this logic, that generator having lowest droop characteristic will have the maximum loading, okay. And if by chance there is a ideal generator and all are non-ideal, then in that case ideal generator will share all the loads, okay. Remember this thing, ideal generator will share all the loads. And similarly remember this two area frequency also, okay. Two area frequency, for two area frequency remember this formula, okay. And here only new thing is beta, okay. Beta 1 beta 2 means beta for this one, beta means nothing, just a b plus 1 by r1, okay. And here we had no b plus 1 by r, this is beta, okay, this is beta. And a is, and a12 is s1 upon s2 or p1 upon p2, or a21 means p2 upon p1 or s2 upon s1, okay. Remember this is very simple logic, okay. So let us see one simple logic of this two area criteria, okay, two area frequency control, okay. And in two area frequency control there are methods of frequency control like flat frequency control, flat tie line or flat base control, and third one is flat frequency parallel frequency control. Okay, in case of flat frequency control, there is disadvantage that in case of flat frequency control there is disadvantage that suppose this one is generator 1 and 2, and here we have Thailand, and if there is sudden change in load, okay, if there is some sudden demand increase in load, okay, and this generator could not respond quickly due to some reason, then all the demand is taken from this generator. Okay, if the load demand is low or normal, in that case it is okay, but if load demand is very high, in that case this Thailand will have more stress, okay, because so many load will flow through it. Okay, so this will get more stress, and if it get more stress, then the circuit breaker will operate, and this will isolate the tie line. Okay, this is the disadvantage of this flat frequency control, means it will start taking load from another generator also. Okay, in case of parallel and tie line, what happens is that in case of flat frequency control, tie line gets loaded, and so circuit breaker might operate. In case of parallel frequency control or flat tie line loading remains constant with increasing load. Okay, if load increase, it will not take from here, it will take from here only. Okay, this is the because there is parallel frequency controlling. Now let's study traveling wave or transients in transmission line. Due to lightning surge, transients occur due to inductance and capacitance. Because transients does not occur due to resistance and conductance, so we neglect it in the analysis, and if we neglect these two parts, then transmission line will become lossless. So we can say that we will do an analysis of lightning surges using lossless transmission line. Okay, so due to L and C, there is continuous transfer of energy from L and C happens, and we know that energy for L is given by half Li square, and C is given by capacitance given by half Cp square. When we do this, after that we'll get V upon I equals to root L1 C1, and this is also equals to Z. So this is only the surge impedance. From here surge impedance is derived. Okay, and we know that for overhead lines surge impedance lies between 300 to 500, but generally we take it 400 ohms, and for cables it lies between 40 to 50 ohms. And in this, what we need to remember is the most basic thing about this topic is that suppose this one is a transmission line of impedance ZS. Okay, and we have load ZL. If surge will happen out here, lightning surge is a very high magnitude. Okay, very high voltage, so all the voltages will not pass to the ZL. Okay, because load means it will accept very limited amount of voltage and current so everything will not pass. Okay, so this one is incident. V and I is lightning surge, and this is incident. Okay, incident signal. Okay, some of them will pass and some of them will reflect back. Okay, the voltage and current that will pass through it and pass through the load, that is known as incident. That is not as known as transmitted or refracted, and is represented by V double dash and I double dash. And voltage and current that is reflected back and is known as reflected signal, that is V dash and I dash, and this direction will be this. Okay, if you want to put this direction then we have to change the sign of V and I. Okay, V dash and I dash. So we have done this. See, okay, so remember these terms. Okay, remember these terms. This is transmitted or refracted coefficient of voltage, and transmitted or refracted coefficient of current, and this is reflected coefficient of voltage and reflected coefficient of current. Okay, these terms you need to remember. And this means transmitted coefficient of voltage means transmitted voltage upon incident. Okay, transmitted voltage upon incident voltage. And similarly for current also, transmitted upon incident. And similarly for reflected voltage means reflected voltage upon incident voltage. Okay, this is the coefficient. Okay, these things. And and the relation between coefficient is very important. Okay, it will help you to solve many problems in exams. Okay, so these relations are very easily we can derive it by ourselves also. Okay, let us say for transmitted voltage, you know that v double dash upon I dash. Okay, v double dash means what? I double dash into zl. Okay, I double dash into zl, and this one means I into zs. So I double dash upon I will become ti, and this will remain as it is. Okay, this is what we got. And this one is 1 plus rv. Okay, this one we can prove by v dash. See, from here we can prove that. Okay, see, we know that v double dash equals to v plus v dash. Okay, from here we can prove this way. Okay, and from the relation of current we can prove for transmitted current. Okay, transmitted current, transmitted coefficient of current equals to 1 plus reflected coefficient of current. Similarly, transmitted coefficient of voltage equals to 1 plus reflected current of voltage. This thing you need to remember. Okay, remember, this is very easy. And here we have for rv we can do like this. Okay, rv reflected coefficient of voltage equals to minus reflected coefficient of current. Okay, this thing you just remember this. Okay, because see, this one we can prove by this way. Okay, just put this value. Okay, after putting value, zs will get cancelled. And why this minus sign came here? This minus sign came here due to phase shift due to L and C component. Okay, that's why you have minus sign out here. And similar kind of thing you will okay, so this one also we have already proved. Okay, this thing you need to remember. These relations is very important. Okay, these relations you need to remember. And when we talk about case 1, suppose we have this. Okay, transmission line, and after that it has ZL is connected in parallel. Okay, ZL is connected in parallel. This type we have. Okay, so for this TV is this one you need to remember. For this TV is 2 upon Z1, that is this one, Z1 upon 1 upon Z1 plus 1 upon Z2 plus 1 upon Z3. Okay, this way you have to do. And this one also we can derive it very easily. Okay, this one is very easy to derive. See, Ti2 means what? Ti2 means I2 double dash upon I. Okay, so I2 double dash means what? V double dash upon ZS1. Okay, see, this one you can prove this way. Okay, see, after that these two will get cancelled. Okay, so finally nothing will get cancelled, but this will remain, this will become TV, and this will remain as it is. Okay, similarly we have proved this also. This is very easy, we can prove in exam also. Mainly you need to remember this one from this case. Okay, remember this formula. And when we talk about case 2, it is nothing but just we will open this Z3. Okay, just open this, means Z3 open means Z3 will be infinite. Okay, after that we will just put this value. See, from here, after getting TV we can calculate for all the parameters. Okay, all the parameters very easily we can calculate. That we can do by, if you remember this relation. Okay, if you remember this TV and RV relation. See, after getting TV we can easily find RV. Okay, after getting RV you can easily find RI. Okay, because RV, okay, just minus sign is difference. Okay, so after getting RI we can find TI. Okay, after getting TI, see, TI, from RI we can get this, and from RI we can get TI also. So in this way we can obtain all the values. Okay, after that you need to remember this thing that if z3 is constant, then case 2 becomes zl is not equals to zs. Okay, in that case see, you just have to put z3 equals to infinite in this. Finally we will get this equation. Okay, and after getting tv you can easily find rv. Okay, this you do not have to remember, just you need to remember this and relation. And after, if this one is infinite, just put this value out here. And similarly we can do for zl equals to zs. Okay, if zl equals to zs, it means that all the signal will pass. Okay, there will be no reflection kind of thing, so reflection becomes 0. See, reflection part is becoming 0. And if zs equals to zl means vr will be equals to vs. And remember that in this case vr will be equals to vs, but vs will lead vr by beta l. Okay, beta l, and ir will lead and is will lead ir by beta l, but their magnitude will be equal. Okay, remember this is special things that we need to remember. So remember this, and this case is called, if zs equals to zl, then flat voltage and flat current profile and power factor is 1. Okay, and a flat line or infinite line, this is also called flat line or infinite line. Okay, and if you are given in the question, if you are given vr value, you are given beta and length of the transmission line is given. Okay, beta value is given, length of transmission line is given. Okay, we can find ir equals to ir by vr upon zl. Okay, zl will be also given. Okay, and zs will be given, and beta l will be given. Okay, so finally we can find vs, and is also we can find this way. Okay, this formula you need to remember. Okay, and we already know that SIL formula is vs square upon zs, therefore loading formula is this. Okay, and we know this relation, we have already studied previous. If SIL equals to loading, then UPF power factor will be there, and VR equals to vs. Okay, and SIL is greater than loading than leading. Okay, in that case we connect inductor. Okay, in that case we connect inductor. Okay, vr is greater than vs, then we connect capacitor. Okay, and inductor we connect. And in case of SIL is less than loading, then that's the case of lagging. It means that okay, here we connect capacitor in shunt to make it equal. And case 4 we have if zl is 0 means short circuit. Okay, we'll just put this value in the case 1. Okay, we'll just put this value and we'll finally get these values. We can easily find these things. Okay, you don't have to remember this. And similarly for open circuit also we can find out. Okay, and remember this one, if we connect inductance, and if we connect capacitance, we know that inductance inductor do not allow sudden change of current, but it allows sudden change of voltage. Okay, as soon as the surge will occur, immediately voltage will rise to 2 per unit. Suppose surge is of 20 kV, then voltage across inductor will immediately be seen as 40. Okay, into 2. Okay, we have this kind of curve. Okay, and after some time it will become 0. Okay, this formula we have already studied in network. Okay, this inductor will getting discharged. Okay, after the surge it will charge and it will discharge. After getting discharged, voltage across this will become 0. Okay, after getting discharged, voltage across this will become 0. And so remember this thing. And if we connect capacitor, then we know that capacitor do not allow sudden change of voltage. Okay, so at the time of zero, at zero time it will be 0, and gradually it will increase to 2 per unit. Okay, it will gradually increasing to 2 per unit, and if it is 20, then it will increase to 40. Okay, so in this way we have the relation, and this also we know that it is the case of charging of capacitor. Okay, v into 1 plus e to the power minus r minus t by rc. Okay, and here we have minus t by zs. R means zs and c means c. Okay, so this is the case of discharging of inductor, and this is the case of charging of capacitor. Okay, this thing you need to keep in mind. Now let's study about switch gears and protection. In switch gears and protection, basically we need to study about different types of relays, circuit breaker, that helps to protect the different types of equipments present in the power system. Okay, suppose if there is no fault, basically the basic diagram of relay and circuit breaker combination is this. Okay, this one is the basic diagram. Sorry, this one is not this one. Okay, relay and circuit breaker. Okay, so in this, basically what we need to remember is that relay operating time, circuit breaker mechanical time, and arcing time. Okay, suppose if there is no fault, suppose if there is no fault, so this one circuit breaker will remain closed. Okay, okay, so circuit breaker will remain closed, and TD, that is driving torque will be less than or equal to the restraining torque. This is a spring. Okay, this is restraining torque, this is driving torque. Okay, driving torque will be less than. Okay, suppose here we have the sequence. Very easily we have explained this sequence out here. Okay, let us see this. Okay, let us see this. Let's see. When we talk about, suppose if there is no fault, blocking condition means TD is less than or equal to, means driving torque is less than or equal to restraining torque. Suppose if fault occur, okay, suppose if there short circuit fault occur, then primary current will increase. Okay, primary current will increase. If primary current of CT, this is primary current of CT, obviously. Okay, primary current will increase, therefore IS will increase. If IS increase, then this coil will get energized. Okay, if this coil energized, then TD will increase. Okay, if TD will increase, if TD is increased, and it is increased in such a way that it becomes greater than the restraining torque, then this strip contact will close. Okay, if this strip contact will get closed, then this I1 will not be equals to 0, and if it is not equal to 0, then trip coil will get energized. If this trip coil energized, then circuit breaker opens, and after opening of circuit breaker, arc is formed here. Okay, and remember that current will flow till arc is there. Okay, current will stop only when arc is stopped. Okay, so all together forms, finally we have relay operating time, fault, instant of fault to the closing of trip coil. Okay, it is relay operating time, and circuit breaker mechanical time is closing of trip coil to opening of circuit breaker, that is circuit breaker mechanical time, and arcing time is opening of circuit breaker to quenching of arc, and quenching of arc is, it is done through using vacuum or SF6 gas, oil, or sometime air also. Okay, so this way we do. So this one is arc quenching time. Okay, there are 3 times. Okay, so when we combine circuit breaker mechanical time and arcing time, then this forms a total interrupting time of circuit breaker. Remember this is asked in exam. Okay, what is interrupting time of circuit breaker? Then we have to say it is a time, and it is an instant when tripping coil is closed. It is instant time when tripping coil is closed and arc is quenched. Okay, Okay, tripping coil is closed and arc is quenched till the arc is quenched, that is interrupting time of circuit breaker. So we understood the basic working of relays and circuit breaker. Now let us see different types of relays. Okay, we have directional relay, directional relay, also called reverse power relay, directional relay, non-directional relay, or that is called overcurrent relay, and directional relay, that is directional overcurrent relay. Okay, directional, non-directional, and directional overcurrent. Okay, in this basically we have the difference is that when you talk about directional relay, it depends only on the direction. It will not bother about the magnitude. It will only see the direction of power flow. Okay, if the direction of power flow is wrong, then it will get trip. Okay, and when you talk about non-directional relay, it basically depends upon the intensity of fault current. Okay, fault magnitude. If it is very high, then it will trip very fast. Okay, and non-directional and directional overcurrent relay, and this will see the direction and magnitude both. Okay, this will see direction and magnitude both. So remember that, and these are ID. This relay is of IDMT characteristic. Okay, IDMT characteristic means operating time of relay is inversely proportional to the intensity of fault current. Okay, if intensity of fault current is very high, then it will operate very fast. If the intensity of fault current is low, then it will operate slowly. Okay, that is called IDMT characteristic. Remember this, and this graph is between fault current, that is full load current to the time of operating time. Okay, and we have this type of curve. Okay, they have this type of curve. Remember this. So let us see for directional relay, driving torque is directly proportional to Vs is cos theta s minus tau, and if tau is 0, then we have this characteristic. Okay, we have tripping out here, tripping, and blocking. Okay, this thing, and when tau is also there, then we have this characteristic. Remember, this characteristic is action exam. And when we talk about non-directional or overcurrent relay, we have Td directly proportional to If square sin theta, and we have this type of characteristic. Okay, and when we talk about like where these relays are placed, okay, let us see. This directional relay is placed at a generator. Okay, generator. Suppose we have synchronous generator and we want to take active and reactive power from that. Okay, so we will connect a relay there. This relay will ensure that generator will only give active and reactive power. Okay, suppose in the normal case, obviously this generator is giving active and reactive power. If there is any problem in the prime mover of this generator, and excitation is okay, so in that case what will happen, prime mover is disconnected and excitation is there, and this is an infinite bus bar, so it will start taking active power. As it starts taking active power, then this relay will get trip. Okay, and then this relay will get trip. In this way it will protect the generator from becoming motor. Okay, if prime mover is stopped, then it will start to become synchronous motor, that we don't want. Okay, that's why we have connected this directional relay. And when we talk about non-directional relay, that is overcurrent relay and directional and OC and DOC. Okay, OC and DOC, we have very nice application. Okay, this one to understand this, just see this. Okay, OC is always at the end. Okay, see OC, this one is OC. Okay, this one is OC, is always at the end. See, it is at the mainly it will be surely at the source side, and sometimes it is also at the load side. Okay, load side. And DOC is always in between. It will only see the transmission line. Okay, DOC will only see the transmission line, and OC will see both transmission line and source. Okay, OC will see both side. Okay, and in this question is asked in exam, like to find the backup relays of any okay, to find backup relay and also the sequence of operation. Okay, a better practice as many as questions related to this. Okay, we have many questions. Okay, questions is asked from this part and this part. Okay, this one you need to remember, this is formula, and TMS is like time grading. Okay, TMS is time grading, or we can say time multiplier setting, time multiple setting, and this is plug setting, multiplier. Okay, plug setting multiplier and time multiplier setting. Time multiplier setting also called time grading, and this is also called current grading. Time grading is used to provide time delay to the circuit breaker. Okay, sorry, no, time delay to the relay. Okay, it is used to provide time delay to the relay, and PSM is used to increase or decrease the rating of circuit breaker, because load also keeps on increasing according to the demand of customer. So accordingly we have to vary the PSM. Okay, PSM, we accordingly have to vary the PSM so that fault is recognized. Okay, and this one is pickup current. Okay, pickup current is equal to percent PSB into secondary current of CT. Okay, and PSM is fault current upon IPK, that is pickup current into current CT ratio. If there is no CT ratio, then instead of CT ratio we can use load current upon IPK. If we use this, then we finally get IF upon IL. Okay, fault current upon load current. Okay, and remember this time of operation of relay is TMS into time corresponding to PSM. From this we will get from the table or from IDMT graph. Okay, time corresponding to PSM, and also it is equal to K1, that is constant, K1 K2 is constant. Okay, K1 into TMS upon PSM to the power K2 minus 1. Okay, this thing you need to mainly this formula is very important. These two formula, regarding this formula question has been asked many times. Okay, remember this, and this question related to this. Okay, very important. And IDMT, we know that very well how it is. Relay operating time is inversely proportional to fault current. Okay, this graph. When we talk about unit protection relay, a relay that will protect only a particular unit. Okay, like example is differential relay, Buchholz relay, overflux relay. Okay, and when you talk about non-unit protection relay, that is OC, DOC, direct distance relay. Okay, it will not only protect the particular unit, it will also protect the equipments around. Okay, now let us see another important relay, that is differential relay. Okay, differential relay and percent differential relay, also called balanced, biased, or merge price relay. Okay, let us see differential relay. It is basically, it will ensure that windings incoming current is equal to the winding outgoing current. If it happens, if this condition happens, it means that there is no fault current flowing in the from the winding. Okay, and it is basically used to protect the windings of a generator or a motor. Okay? Generator, motor, or a transformer, like whatever, like it is used to protect the windings. Okay. So suppose we have this generator winding and we want to protect this, so we will connect this differential relay. We have two CT. Okay, prime CT1 and CT2. Okay, in this way we will connect the CT. If we connect the CT, then current will flow in this also. Okay, so secondary current will flow. So these two currents should be equal. Okay, if these two current are not equal and these two current are not equal, it means that there is something fault out here. Okay, and if it is equal, then obviously then I1 minus I2 will be equals to I1 minus I2 will be equals to 0, that is IR. Okay, if this is not equal, then current will flow in this operating coil, and when current flow in this operating coil, then circuit breaker will trip. Okay, then the relay will get trip. Okay. So we have same thing. Okay, we know that I1 we can easily find I1 upon CT ratio. Okay, I1 upon CT ratio. Similarly, this I2 upon CT ratio, this I2. Okay, so I1 and I2 so is equal to this. Okay, and IR is 0. IR is 0 in case of ideal. Okay, IR is 0 ideally, but it is greater than I0. I0 is minimum of I0 is minimum pickup current. Okay, I0 is minimum pickup current. It is greater than IR is greater than I0. Okay, practically for the tripping, this is a tripping condition. For ideally it is not equal to 0, and this one is greater than I0 practically. Okay, and blocking is IR equals to 0 ideally. Okay, so this thing, and remember this characteristic also, very important characteristic. Okay, so tripping is above and below is blocking condition. And there are certain disadvantages of this relay. The maloperation of relay happens in case wrong connection of pilot wire. Okay, wrong connection of pilot wire means this is connected in this way. If this wire is connected here and this wire is connected here, that is wrong connection of pilot wire. In this case relay will maloperate. Okay, and difference in resistance of the pilot wire. Suppose we have these two pilot wire. Okay, these two pilot wire, if there is difference in the resistance, if there is difference in the resistance, then also relay will get trip. Okay, in that case also relay will get trip, that we don't want. Okay, and also CT core saturation. If the core gets saturated, then also there is problem. And ratio of phase angle error, if there is phase angle difference, then also IR will flow. Okay, it means fault will occur and relay will get operated. And initial charging time of transformer or doubling effect. We know that initially when we give current to the transformer, it will absorb lots of current. Okay, so in that case, to avoid this tripping, we use HRR. Okay, HRR. Here HRR means harmonic resistant relay. Okay, in differential relay, finally remember this formula. Okay, IR equals to I1 minus I2. Okay, just remember this formula and this condition. Okay, and remember this diagram and this characteristic. That's all. This is the main important thing. And when we talk about differential percentage differential relay, there is nothing. Okay, if you know this, then you can also remember this. This is very easy. Only difference is that this restraining torque is extra out here. Okay, restraining torque we have to use. Okay, and the formula, only change in formula is we have to find the IR in same way. Only change will be out here is that that I0 will be added to some factor, that is K into I1 plus I2 by 2. Okay, K into I1 plus I2 by 2. Okay, conditions will remain same. Okay, trip and block condition will remain same. Okay, but only difference will here that I0 will get increased. Okay, if I0 increase, then obviously then the blocking area will increase. See, blocking area got increased. Out here we have this much blocking area, but here area is increased. Okay, this after using this, this percentage differential relay, we can avoid maloperation or due to various causes. Okay, that we studied out here. Okay, wrong connection, difference in resistance, CT ratio saturation, CT core saturation, ratio or phase angle error, initial charging of time of transformer. Okay, this thing we can avoid. Okay, and remember this thing. And here what we need to remember mainly is K value. K value is NR upon N0. Okay, NR is what? NR is NR upon NO. NR is resistance turns of resistant operating coil. Okay, resistant operating coil, restraining operating coil turn, and this one is operating coil turn, and this is restraining coil turn. Okay, nr upon no, and this one is given by ir upon i1 plus i2 by 2. Okay, this thing you just remember the k value, and instead of k we can be given as percentage slope, percentage difference. Okay, percentage difference or percentage PSB setting. Okay, this thing you might be given in the question, so remember this. Okay. So in this thing, this percentage differential relay helps to protect three-phase generator winding, three-phase transformer, and also a bus bar. Okay, when we talk about three-phase transformer, here we need to remember some few things to avoid tripping due to 30-degree phase shift. Okay, to avoid 30-degree phase shift, what we have to do is, suppose we have transformer of star delta, then we will use CT of delta star. Okay, just opposite of transformer. Okay, and if we have transformer of delta star, then we will use CT of star delta. Okay, suppose okay, this thing you need to remember. And if it is star star, then delta delta, and if it is delta delta, then star star. This thing you need to remember in three-phase transformer. And next we have a restricted earth fault relay. Restricted earth fault relay, we have to remember percentage winding that is unprotected is equal to percentage winding that is unprotected equals to in upon in into rn upon vph. Okay, that is phase voltage into 100. And if we get this if we get winding protected, then we can find if we get winding unprotected, then we can find winding protected by 100 minus percentage winding unprotected. Okay, and in is given by, and this in is equal to minimum pickup current into CT ratio. Okay, if we can also be given instead of minimum pickup current as out of balance current. Okay, out of balance, or if CT ratio is not given, we can take the generator full load current. Okay, remember this winding unprotected. To understand this, let us see restricted earth fault relay. Here let us understand winding unprotected relay and winding protected relay. Suppose this is the windings. Okay, winding R, Y, B, these are the winding of generator. Okay, suppose fault has occurred out here. Okay, suppose fault has occurred out here. Okay, in this case what will be the fault current? Fault current will be till here VGA. Okay, suppose this one is A point and this one is B point. Okay, this one is B point and this one is A point. Suppose fault occur at A, so VGA out here, from here to here, voltage will be more than the voltage than this to this. Okay, so VAG upon IXG till here reactance, and this Rn will remain same in both the cases. Okay, in both the cases Rn will remain same, only will vary is VGB and VGA. VGA will be more than VGB, and XGA will be more than XGB. Okay, so similarly we can say that if will be less. Okay, if will be less, then IFB fault at B point will be less than fault at A point. If it is less, then the relay might not operate. Okay, if the current is less, then relay might not operate. So if fault occur here, then relay will not operate. It means that this much winding is unprotected part. Okay, so this is what unprotected, and this one is protected. If fault will occur out of this part, then relay will operate. Okay, so this one is unprotected, so that's what percentage unprotected is given by this formula, and percent protected. And we know very well about overflux relay. Flux means what? Flux density is B upon A. okay. V upon f, if f will decrease, then flux density increases, okay. If frequency decreases, then flux density increases, or if voltage increases, then flux density increases, okay. So this one is V by F at the fault current, at the fault. If it is greater than K into V upon F, V upon F, and for 120 second, then then relay will trip. Otherwise, if it is less than or equal, then it will block. And K is between 1.1 to 1.3, and N is nominal, and F is fault, okay. Remember this. And a split phase relay, this relay helps to detect current difference in parallel wire of same phase. Suppose we have to transfer very high huge amount of power. In that case, what we do is we use parallel conductors, okay. We use parallel conductors. So to ensure that all the conductors are healthy, so to ensure that all the conductor operates in healthy manner, we use a split phase relay. If either of the conductor will get faulted, it means that other conductor will get overloaded, and that also might get damaged. So to prevent this condition, we use a split phase relay. Suppose we have two conductors passing by, okay. Suppose we have two conductors. We will connect CT there, then we will connect a CT back to back CT is connected this way, okay. And here relay will be there, okay. If the current flow through is not equal to 0, ideally relay will trip, okay. This thing you need to remember. And universal torque equation is this one, okay. This is driving torque, then this one is over current, then over voltage, and this is directional, okay. K3 VI cos theta minus tau, directional. And this one minus spring restraining torque, okay. This one, okay. So this one is universal torque equation, okay. Now let's study about distance relay. In distance relay, we have impedance relay, Moho relay, and reactance relay. Impedance relay is voltage restrained over current relay. And distance relay is basically work on the principle impedance is directly proportional to the length and is directly proportional to the distance, okay. And these are of three types, that is impedance, Moho, reactance. Impedance relay is also called voltage restrained over current relay. It is used in medium transmission line. And remember this characteristic of this, okay. This one is for non-directional locus of non-directional impedance relay, okay. This one is locus of non-directional impedance relay, and this one is angle impedance relay, locus of angle impedance relay. When we talk about locus of directional impedance relay, this part will not be there, okay. This one will be also blocking case, okay. This one will be the case of blocking, okay. Only this part will be the tripping, okay. This part with the tripping, blocking. This one will be also blocking, okay, in case of directional, okay. Only difference is that. And here we need to remember that this condition, if you assume from the universal torque equation, if you assume K3 and K4 0 and K2 minus, then you will get this torque equation, okay. And remember this root K1 upon K2 is ZL, okay. Root K1 upon K2 is ZL, and this one V upon I is ZF. And if ZL is greater than ZF, then trip will occur. If ZL is less than or equal to ZF, then trip will not occur, that is blocking case, okay. So in the same way, we have to remember this also, okay. Just remember this this condition, okay. This condition, and we already know the universal torque equation, so from there we can find out this, okay. And this one is same for all, okay. This tripping and blocking condition is same for all. ZL, if ZL is greater than ZF, then tripping will occur. If ZL is less than or equal to ZF, then tripping will not occur, then blocking case. And remember this, okay. And remember this characteristic. For Moho relay, it is used in long transmission line or power switching is frequent. If power swing is frequent, in that case we use. And distance relay with inherent directional property is Moho relay. This has been asked 2 times in GATE exam. Distance relay with inherent directional property is called Moho relay. And reactance relay or X relay, here we have to assume this R2 equals to R4 equals to 0 and K3 is minus, okay, and condition is same for tripping and all, okay. So this one is the characteristic, and it is used for short transmission line, and also arcing ground is frequent. When arcing ground is frequent, in that case we use this, okay. So remember this. And 3-zone protection transmission line, okay, this one 3-zone protection transmission line also increase the stability. And pilot relay current carrier protection, okay. And this one, suppose we have any particular relay, and we have 3 zones of transmission line. This relay will protect 80% of the first zone, 50% of the second zone, and 20% of the third zone. In this way, all the relays will operate, okay. All the relays, like in second zone also there will be relay, and this relay will protect the 80% of this, 50% of this, and 20% of another, okay. So in this way, sequentially, we can obtain very good stability, okay. So we use this, and this one is used only below 33 kV, okay. And circuit breaker, when we talk about circuit breaker, in this remember that this vacuum circuit breaker, SF6 circuit breaker, oil and air, these are old method, okay. This nowadays this one is not used. And vacuum circuit breaker is used up to 33 kV, and above 33 we use SF6. When we use SF6, this is a quenching medium, okay, arc quenching medium basically. And in circuit breaker, basically you need to remember about natural current 0, force current 0, that is current chopping, and high resistance interrupting current. In case of high resistance, this one is for HVAC breaker, HVAC circuit breaker, and this one is DC breaker, okay. High resistance interruption, high resistance in interruption. This one is used in DC circuit breaker. So okay, in this, basically what we do is we connect a resistance across the circuit breaker when we are about to open that circuit breaker, okay. So that arc is so it will it help to reduce transient, okay. It helps to reduce transient. Resistance is connected in between the circuit breaker, and that resistance value is given by half root L upon C. And this one is FD. FD is damping natural frequency, is given by 1 by 2 pi root 1 upon LC minus 1 by 4 R squared C square, okay. Remember this. And for force current or current chopping, you need to remember this equation, okay. Here this one is used where no load power transformer takes low magnetizing current. In that case, due to energy exchange between L and C, huge voltage is developed, okay. And that voltage is given by and we know that like energy of L is half Li square, and energy of voltage is energy of capacitor half CB square. So when we will do equal, and finally we will get this, okay. VCB, voltage across circuit breaker, is IA into root L upon C, and unnatural frequency is given by 1 by 2 pi root LC, okay. And natural current 0, okay. This one is used for HVAC breaker and used at no load or full load, okay. And this one is IMK, that is maximum current at closing of circuit breaker, and this IBK is maximum current at opening of circuit breaker. Okay, and this one relation is given by IMK is equal to 2.55 IBK. This one is in RMS. Okay, this one is in RMS, and SBK, this is capacity at braking. Okay, capacity at braking. So if you know IMK and IBK correspondingly, we can find braking capacity, that is given by SBK root 3 VL IBK, and making capacity, that is root 3 VL IMK. Okay, and remember, this one is the most important formula. Okay, so this one is the most important formula, re-striking voltage or transient recovery voltage, TRV. Okay, recovery voltage, this one is the most important formula. Like what is re-striking voltage? Huge voltage that occurs due to energy exchange between L and C of a line, transmission line, is called re-striking voltage. Okay, huge voltage that will occur across a circuit breaker due to energy exchange between L and C. And TRV formula is given by K1 K2 K3 Vm into 1 minus cos omega and T. Okay, mostly this K1 K2 K3 value is not given. Okay, so if this value is given, then we will take, otherwise we will take it is 0, and instead of this value we might be given for K1, we might be given this K1 is first pole of clear factor, and K2 is armature reaction component, and K3 is sin theta, where theta is load power factor angle, and we will take 1. If power factor is 1, then we will take K3 as 1. Okay, and if it is given grounded fault, then we will take K1 as 1, and if it is ungrounded fault, then we will take K1 as 1.2 or 1.5. Okay, this thing you need to remember. And instead of K1 K3 value, instead of K1 value, we might be given as like for grounded fault or for ungrounded fault. In that case, we have to take this. Okay, for grounded it is fixed that it will be 1, and for ungrounded value lies between 1.2 to 1.5, and for K3, if it is unity, we will take 1. Okay, let us suppose all these values are 1. Okay, all these values are not given, and we are taking it 1. Okay, so in that case, if we have to find TRV maximum, transient recovery voltage maximum, so in that case what we will take is 2 Vm. Okay, this one to make this, what we have to do is we have to make it 0. To get TRV maximum, we have to make it 0. To make it 0, to make this value we have to make this -1. To make this value -1, we have to take omega and T equals to pi. If we take omega and T equals to pi, then we will get T value. T value equals to pi root LC. Okay, pi root LC. So this maximum TRV occur at time equals to pi root LC, and this one is given by 2 Vm. Okay, and we can also write it as this one is maximum value. Now then we will convert it into RMS. Okay, after that we will convert it into line. So after doing all this, we will get 1.632 VL RMS. Okay, so similar. Next we have rate of rise of TRV, that is transient recovery voltage, that is RRV. Okay, you don't have to do anything, you just have to take a derivation of this part. Okay, after taking derivation, you will get this Vm omega and sin omega and T. So finally we can write it this way. Okay, Vm upon root LC, because omega n equal to 1 upon root LC, so root LC. Okay, and this one an RRB and RRB maximum will occur at when this part is 1, and this part can be 1 only when omega and T equals to pi by 2. Okay, and so similarly we will get T value, T equals to pi by 2 root LC, and for average RRB value, we can find TRV maximum upon time. Okay, TRV maximum upon time at which TRV maximum occur. Okay, this we have to take for average. And finally we have HVDC. In HVDC we have to remember very few things, like as pulse number increases, number of harmonics will increase but its magnitude will decrease. Okay, that's why we will prefer more number of pulse only, because harmonics will increase, that is okay, but its magnitude is very low, that's why it will not affect much. And PIV and we prefer PIV upon VDO. VDO is nothing but it's a it's average DC voltage of average DC voltage output of a converter, and it is given by 3 root 2 upon pi VL, that is line current of AC. Okay, and PIV is peak inverse voltage, and PIV upon VDO should be low, and VDO upon E should be high. Okay, and E is a peak current of AC. Okay, and this is TUF, transformer utilization factor should be unity. Transformer utilization factor should be unity. And in converter transformer, T1 is star grounded and star to avoid circulating current, and T2 is star grounded with delta to get 30-degree phase shift. Okay, we have certain advantages of using this. And remember that negative polarity has less corona and less radio interference, so it is taken as physical conductor, and positive can be taken through the ground. Okay, for monopolar link, negative polarity is taken from conductor, and positive is through ground. And for bipolar, negative and positive both are carried through conductor, and this one is most practical. And homopolar, and for homopolar, two negative polarity with a common both are negative polarity, and positive polarity we take from the ground for homopolar link. And HVDC is used to transfer bulk amount of power for long distance, even with substation having different frequency. Okay, if it is of same frequency, then also we can transfer, and if it is of different frequency, then also we can transfer in case of HVDC. In case of HVAC we cannot do so. In case of HVAC we cannot transfer power through the substation having different frequency, but in case of HVAC we can do so. Per phase conductor power transfer in DC is 48% more than in AC. Okay, and power transfer by 3-wire AC HVAC is equal to the power transfer by 2-wire HVDC. Then obviously the losses will be less now. So power loss in HVDC is 66.7% of power loss in AC. It can't operate. Only disadvantage, there are certain disadvantages also, that it cannot transfer active power in the line, and convert and also converter absorb reactive power from the AC. Okay, it cannot transfer reactive power in the line, and converter absorb reactive power from AC. We can't take tappings okay in between. And circuit breaker is costly because the magnitude is constant. Okay, it will never become zero like AC. So operation of circuit breaker should be heavy, and it become costly. And ID, that is transmission line current, is given by VDOR cos alpha minus VDOI cos beta upon R plus RC R plus RCI. Okay, this you can understand from this diagram, from this equivalent circuit of HVDC with beta control mode. Okay, this one is a rectifier. Okay, for rectifier, and this one is inverter. Okay, so accordingly we have VDOR cos theta and VDOR cos beta. Okay, sorry, this is alpha, cos alpha. Okay, this is the thing you need to keep in mind. Very simple things. Okay, and one important thing that we need to keep in mind is For HVDC back to back connection, we have this, okay, synchronous link. This one is synchronous link, and this one is asynchronous link. Asynchronous link can only be possible with HVDC back to back, okay. We cannot use HVAC line in between a substation having different frequency. If it is of same frequency, then we can use either AC or DC, but we prefer to use HVAC and together with HVDC also, because it will provide the because HVAC is constant, okay. See, this delta is constant, this all things are constant, but but we can increase the power by increasing DC power, okay. Part of total power is controlled by DC system, okay. So it will increase the stability if we connect two substation this way, no. In this way we can increase the stability, remember this. See here, this one is for HVAC line and this one is for HVDC line. Initially HVDC is very costly due to converter and all, okay, but after 400 kilometer HVDC become cheaper than HVAC, okay. Also remember this graph, okay. Also remember this graph, why we prefer HVDC for long length. See, from here you can understand P equals to for HVAC, P equals to VS VR upon XL sin delta, and these all things are constant. So IL and theta and delta is also stability constant. So power transfer is inversely proportional to length, okay. If length increases, then power transmission decreases, okay. And it will its graph is like this, but for HVDC graph is this one, okay. For any length HVDC power will remain same, okay. That's why we prefer HVDC for longer length. Now let's study generation part from this thermal power plant. This is a layout of thermal power plant, coal waste thermal power plant, okay. When we talk about principle of working, it work on the principle of Rankine cycle, okay. And let us study this, okay, stepwise. First of all, water is given to the hot well, and this water is demineralized water, and its pH value is less than 9, that is alkaline in nature, okay. This water only we have to use in the power plant, okay. So we are using this type of water, demineralized alkaline water, to avoid corrosion in the tube, and life of the tube will increase, okay. Boiler or tube is same, okay. So pressure in the hot well is 1 kg per centimeter square, that is this is like atmospheric pressure only, okay. And from the hot well, CEP, that is condensate extraction pump, this the water is passed from hot well to condensate extraction pump. This will increase the pressure to 16 kg per centimeter square, okay. And then it is passed to low pressure heater. Low pressure heater will just increase the temperature to 110 degrees Celsius, and it will and this low pressure heater will get heat from this IPT, that is intermediate pressure turbine, okay, intermediate pressure turbine. So it will get heat from intermediate pressure turbine. So how it is heated, let us see. Some part of this steam, this heated steam, some part of this heated steam will come here, and here we have this pipe will pass through this LPH. Okay, this will like tubular in nature pipe. Okay, and when this steam is injected over here, this pipe will pipe filled with water will absorb the steam heat. Okay, and temperature of this steam is, see, let us see how much temperature is this. Temperature of this steam is around out here it is 340 degrees Celsius. It is more than 340 degrees Celsius. Its temperature is around 450 degrees Celsius. Okay, its temperature is around 450 degrees Celsius. Now it will this LPH will increase the temperature to 110, and remember that we don't provide any type of heating and all out here. Okay, we get heating from IPH, that is intermediate pressure turbine. Okay, and then it is passed to deaerator. Okay, deaerator is used to remove the air molecules from the water. Okay, it will just remove the air molecule from the water, because if there is air molecule in the water, then it may damage the turbine's blade. And then after deaerator, it is passed to the boiler feed pump, that is BFP, that is boiler feed pump. And this boiler feed pump will rise the pressure to 165. Okay, 165 kg. This will increase the pressure to 165 kg, and this is the highest power consuming pump in the whole power plant. Okay, total 3 pumps are used. Okay, 2 are in operational, and one is kept as a backup. Okay, two is always in the operational. Okay, the boiler feed pump. After boiler feed pump, it is passed to the high pressure heater. High pressure heater will receive heat from the high pressure turbine. Okay, we don't use any external heating and all. We just take some part of heat from the high pressure turbine. It has very high temperature, and it will heat the this tube. Okay, this tube passing through this high pressure heater. Okay, high pressure heater, and it will heat the water to 190 degrees Celsius. Okay, it will heat water to 190 degrees Celsius, and it get heat from the high HPT. And after this high pressure turbine, the water will pass to the economizer. Okay, economizer is used on top of this boiler. Okay, this get heat from the fume gases. Okay, fume gases whose heat tends to get wasted. This heat can be utilized by the economizer, so it also helps to increase the efficiency of this boiler. Okay, so economizer will get heat from the fume gases, and it will increase the temperature to 300 degrees Celsius. Okay, due to this economizer, temperature got increased to 300 degrees Celsius. See, out here temperature is 300 degrees Celsius, but water is still in the liquid form, because we know that pressure is if pressure is high, then the temperature required to convert it into steam should also be high. So 300 is not sufficient temperature to convert it into steam, because its pressure is high. Okay, so it is still in the liquid form because of very high pressure. Okay, so after this economizer, it will pass to the drum. Okay, this drum, basically we fill only 50% of this drum. Okay, only 50% of this drum should be filled. In case of supercritical boiler, that is used for 500 MVA of generator and all, in that we don't use this drum part. Okay, in that what we do is, after economizer, it is directly passed to the HTS. Okay, it is directly converted into steam. Okay, it is directly converted into after economizer, it is passed to this tube. Okay, that is walls of the boiler, and it will convert it into steam. Okay, and after steam, this drum part is removed in the supercritical. This is subcritical boiler. Okay, so in this we have drop, and water will get accumulated. Only 50% of water we will accumulate in the drum, and 50% will be steam. Okay, and water falls naturally. See, from here drum, water will fall naturally downward. Okay, for water will fall naturally downward. This is a tube, and this one is on the walls of the boiler. See, this one is boiler. It is like a big room. Okay, and the walls will have the tube, and that tube will absorb heat from this burning coal. Okay, so it will absorb lots of heat, and that 300 degrees Celsius water will absorb more heat, and it will convert into steam. Okay, after it convert into steam, it will pass through this. Okay, it will convert it into steam. After that it is sent to the this turbo separator. Okay, turbo separator, this one is turbo separator. This turbo separator is basically used here to separate the steam and water. Okay, in the same drum. Okay, to separate this steam and water in the same drum. And remember one thing, that only 50% of this drum is filled with water, and 50% is filled with steam. Suppose if we increase the water level, that is, if we increase the drum level height. Okay, if we increase the drum level height, then water might enter in the turbine. Okay, in the turbine, and turbine blade will get damaged. If steam volume is lower than 50%, and then there won't be sufficient water in the tubes. Okay, then there won't be sufficient water in the tube, and tube will get heated, and due to that, in absence of water, tube may get damaged. Okay, that's why we cannot prefer this. Okay, so we have to maintain 50% water and 50% steam out here. Okay, so after that, this steam is further passed to the high temperature superheater. Okay, HTSH, high temperature superheater. The function of this HTSH is to increase the temperature to 540 degrees Celsius. Okay, it will increase the temperature to 540 degrees Celsius, and this one is in steam in nature, and temperature is also increased. Okay, and then this one is fed to the HPGV. Okay, that is high pressure governing valve, and this high pressure governing valve will pass the steam to the high pressure turbine. Okay, high pressure, this governing valve is used to control the steam to the turbine. Okay, and in this turbine, and in this high pressure turbine, the pressure is 150 kg per centimeter square, and temperature is 540 degrees Celsius, and steam flow is 600 tons of steam per hour. Okay, so this is the specification of this high pressure turbine. Okay, and after that this steam will expand out here. Okay, and this steam will release energy by rotating the turbine. So its pressure will decrease. So its pressure will decrease to 28 degrees Celsius, and temperature will also decrease to 340 degrees Celsius. Okay, and then again it is reheated. Okay, reheated again. It is reheated by using ITSH, that is intermediate temperature superheated tube. Okay, intermediate temperature superheated tube. Okay, so it will reheat it, it will reheat the same to 450 degrees Celsius, 450 degrees Celsius, but the pressure is decreased to 26 kg. Okay, because now we are going to use it in intermediate pressure turbine, which do not require much pressure. Okay, that's why its pressure is reduced to 26 degrees Celsius, but temperature is still high, that is 450 degrees Celsius. Okay, then again IPT will receive the heat from IPGV, that is intermediate pressure governing valve. Okay, and so again here so finally we can see that IPGV and GPV can be used to control the speed of this generator, and finally we can control the frequency. Okay, 50 hertz. Also we can speed, if we can control the speed, then we can control frequency also. Okay, so in this IPT low pressure, so in this IPT the steam will further expand. Okay, and it will and pressure will also reduce, and temperature see after that it is passed to the low pressure turbine. Okay, and here pressure released is less than 5 kg. Okay, less than 5 kg and 340 degrees Celsius. Okay, low pressure, and here it will further expand. Okay, the steam will further expand, and its temperature and its pressure will be no less than 1 kg, and its temperature will be 250 degrees Celsius. Okay, such a low pressure, this pressure is less than the atmospheric pressure also. So to absorb heated steam from the LPT, we need to use vacuum to absorb this steam. Okay, because pressure is very low out here. Okay, less than 1 kg, so that's why we have to note we need vacuum. And this heated, see, lots of heat is still there, but we might think that we can use it in the boiler, but we cannot use it in the boiler. Steam it is, its temperature is high, but see its pressure is very low, but we are operating boiler at very high temperature, very high pressure. Okay, that's why we cannot use it in the boiler. We have to, only option is that we have to condensate it condensate it in the form of water, and again it is passed to the hot well, and again same process is repeated. Okay, and this one is this steam is condensated by using the raw water is passed to this tube. Okay, and this cold water will absorb the heat of this steam, and then again it is it will fall in the cooling tower to cool, and again it is cooled down. Okay, this water will cool down, again it will go. Okay, this way condensation process will happen. Okay, so next we have to study about this thing. Okay, see this one, coal hopper and all. Okay, let us see how this we need to put 20 to 30 of coal. Okay, 20 to 30 of coal in the coal hopper. Okay, we will put coal hopper out here, and then it will pass to the mill. Okay, and this mill will convert this coal pebbles into the powder form. Okay, pulverized coal, that is called pulverized coal, powder form. We are converting it into powder form so that coal can burn very easily. Okay, and it will give maximum efficiency. That's why we are doing so. And then this powder form coal is sent to the boiler using a primary air fan, that is PA, primary air fan. We will blow this powder using this fan. Okay, primary air fan. And to burn this coal properly, we will use FD, that is forced draft fan. we know that for burning oxygen is required. Okay, that's why we will pass like atmospheric air into the boiler, so that coal will get burned very easily. Okay. And fume gas that comes out of boiler, fume gas that will come out of the boiler will have lots of acids. Okay, that is called fly ash, that is very harmful for the environment. That's why we need to that's why we cannot release it in the atmosphere. Okay. So we will use so this fume gas, that is fly ash content gas, will pass to the ESP, that is electrostatic precipitator. Electrostatic precipitator basically work on the principle of electric field. See, there will be two positive and negative charge plate. Okay. And fume gas containing ash will have positive and negative charge. Positive charge fume gas will get attracted to the negative plate, and negative charge fume gas will get attracted to the positive plate. In this way they are attracted in the ESP, and then gas is released to the induced draft fan. Okay, induced draft fan will ID, that is induced draft fan will force the gas to the chimney. Okay. And thus it is released in the environment. And in this way, in this suppose if during rainy season sometime coal is moist. Okay. So it will not burn very easily, so we use like air preheater. Okay, air preheater, it will the air that is taken from the environment, no, by PA and FD, that is primary air fan and forced draft fan, the air that is taken, no, it will pass to the air preheater. Okay. And air preheater will heat that air. Okay. And that heated air will pass to the powder, that is moist powder. Okay. And this in this way moisture is removed from the coal powder, and then it is passed to the boiler, so that it can burn very easily. So in this way our plant work. Okay, our plant work.